all the talks are being recorded and also live streamed on YouTube. So if you don't want to be recorded or live streamed, then please let me know in advance, like of your talk. And then we're going to have a few, so there's going to be a break, a coffee break, during the morning session, and then afterwards there's a lunch break. But for the lunch, it's better just to follow the locals because there is no organized lunch. So we're going to go to some places, nearby. There are several places that you can have some light lunch. So I think with that we can start. So the first speaker of today's session is Alejandra Castro from University of Cambridge, and she's going to tell us about holographic aspects of symmetric product orbitals.
Thank you. And you'll keep time?
I will keep it.
Okay, because we're supposed to keep it short, and I want to set up a good example. So thank you so much for the invitation. I'm very happy to be here, and I'm very happy to tell you a bit about my work. Sorry, I have to decide which one will go on the left hand and which one on the right hand. Okay, so before we start, this is a talk with a very long title. I wanted to acknowledge that what I'm going to be telling you today is based on a collection of work that has been happening for, I don't know, close to 8 or 10 years with a variety of people. So here I'm listing my collaborators, and I highlighted in red the most junior people in this collaboration, basically people that don't have permanent jobs yet, but they're fantastic physicists, so I hope you keep an eye on them. But okay, so what is the aim of this talk? What do I want to do? So I want to think that this is an audience of experts, so I'm not going to spend time on introductions and things. But this is a talk about ADS-CFT as the title, as the word holographic means. And I'm going to take a CFT perspective on how to define ADS. And so from that point of view, the main question that I have that is going to be governing this talk is basically try to understand which conformal field theories can capture classical geometrical properties of gravity. Okay? This is the question I have. Okay, I want to understand what are the very specific properties that define that CFTs. Those type of CFTs, I'm going to abuse language, and I'll call them holographic CFTs. Okay? I know there's a sense in ADS-CFT where you would have said any conformal field theory has a dual. It might not be a dual that you want, but just to keep the terminology brief, I will call a holographic CFT basically a conformal field theory whose dual gravity theory has a low energy effective field theory description. Okay? Now, so we all are accustomed to various aspects of ADS-CFT, and so you will tell me, well, some properties that those CFTs needs to have, some of the defining properties are first, that there has to be a large central charge or a large n parameter. Why do we want that? Because in this theory of gravity, there will be black holes, and we need a theory that has a large number of degrees of freedom. We also need what's called a sparse spectrum. This is basically a condition on light operators that are not controlled by n, and this is very important so that I can use the words basically a low energy effective field theory description. So it's tied to that requirement, that I can't have too many fields in my low energy description. Then there's a more fancy condition, the factorization of correlation functions, which also goes under the term that the CFT has a generalized free field description in some sectors, and so on. But the question I have basically is, how many conditions do I need to impose? Here I listed a few that we know are part of what works in the current dictionary and things that we know. But is this all I need to impose? How stringent are these conditions? And basically, if these are the conditions, can I just go and engineer a CFT that meets this criteria? Okay, so having the capacity of doing this really will show us that we understand in and out what ADS-CFT is and how to define quantum gravity via the holographic correspondence. And so I'm not going to give you an answer to this question. This is a really difficult question, and all of these together. But I want to kind of entertain the question. Okay, so let's just kind of dive into it. What would it mean to answer these questions? And so for us, what it meant was like, okay, so you want to engineer CFTs that meet this criteria, pick a CFT that maybe, or a family of conformal field theories that might be interesting. Okay, so here comes the other part of the title, symmetric product orbifolds. And so this is the type of theories, conformal field theories in 2 dimensions that I like. Okay, so what are these theories? They have a very long name, but they're actually not that complicated. So these theories are basically, so the quick definition of them is basically grab your favorite CFT that I'm calling here C, okay, and then tensor it n times. Okay, you do that. What you will get there, so the reason why I'm tensoring my favorite CFT n times is because I wanted some parameter, some large n parameter that I'm going to take to infinity. So I'm going to consider, this is a very easy way how to get large central charge in CFTs. You just tensor the theory again. Now, you know that this is kind of like not a very interesting thing to do. It will not meet, for instance, the sparseness criteria and things like that I imposed. And so in order to remove basically, like if you want to think about it as like the redundancy of like, oh, the positions of the copies are indistinguishable, you basically mod out by the permutation group. So you basically say the positions of the copies should not be important. And so that's what you can view as gauging in this context, okay? And this is what defines CM. So it's basically the tensor product of n copies of the theory modded out by the permutation group, okay? Pretty big name for something that is quite simple. Now, there's 2 things that you need to know about this. So once you do this process of orbifolding, produces 2 types of states then in your theory. You will have what's called untwisted sector states. Basically, they're states that are going to be invariant under the permutation group, and what's called twistor sector states that are basically states labeled by conjugacy classes of the permutation group. If you want, these ones are like gauge invariant operators, and these are things that transform under it. If you want to have an analogy with something like SUN. Okay, very good. Now, why did I pick this? Why is this the type of conformal field theories that I'm going to start asking questions on these lines? Well, there's an appeal because they have a lot of very nice mathematical and analytical properties that allow me to control various aspects of the theory, as I'll highlight. It's familiar, so for those of you that come from a string theory context, but specifically from string theory and ADS3, this is basically the D1, well, various ingredients here show up in the D1, D5 CFT. And there's a utility to them because they have a lot of features that are compatible with ADS CFT, broadly speaking, okay? So this is why we started looking at these type of theories. Now, what I want to do in the rest of this talk is basically I want to understand what do these type of theories teach us about the conditions for having a holographic CFT? So what can I learn about this list of what am I supposed to impose? How am I supposed to construct a holographic theory? And so the way that I'm going to structure the rest of this talk is basically, it's in 2 parts. So I'll first tell you in the context of symmetric product orbifolds, what are differences and similarities with low energy gravity? So how do they look like a low energy theory of gravity and why they don't look like a low energy theory of gravity? And then I'll tell you about how we classify this set of theories. Okay, so let's start with the differences and similarities. So I'm going to bundle them both together. So let's first talk, in this context, what I'm going to summarize to you as I talk about these differences and similarities, I'm basically going to tell you properties of symmetric product orbifolds that are universal. That these are going to be properties that I don't care what you put here as a seed theory. So what are you tensoring? Every single symmetric product orbifold will satisfy these properties, okay? And that's what's going to teach me about how they look like gravity and why they don't look like low energy gravity, okay? So they're very, very universal properties. Okay, So what are the differences with low energy gravity? By the way, you're free to interrupt me with questions since I feel like I'm speaking very fast. Very good.
Can you already tell us how the central charge of this field scales with n?
It's linear with n. It's n times, so if this guy has a central charge, let's say C naught, the total central charge is
So
n.
the scale with n comes from just the number of copies.
Exactly, exactly. So
So any particular reason you didn't choose n to be the rank of some non-abelian group or?
no, this is all the information that you have. It's basically what the number of copies you have. That's it. It's way simpler than gauge theories. I have to specify way less information in this context. So yeah, so the central charge just grows linearly with n, and then you just take n to infinity, and that's what a lot of these computations do. And it's simple as that. Any other questions? Okay. So here are 3 things why these theories are not describing, the duals are not low energy gravity. The first one is that you can have higher spin currents, okay? So for any value of n that is basically bigger than 1, you can construct a tower up to n of higher spin currents, and if n goes to infinity, then you will have infinitely many higher spin currents. So here, I gave you an example of, for instance, the spin 4 current, just so you can have an idea of like how do you construct this higher spin current. So here, Ti is the stress tensor of a single copy, and basically you square it, okay? But you can do that in any CFT. So for instance, these first 2 terms here, it's something that you can write in any given CFT, but this is not a primary. This will be a descendant of the stress tensor. And what's special in symmetric product orbifolds is that you can add a term where you have terms that are in different copies, and this allows you to basically build a primary that is a spin 4 primary, okay? And then you can imagine, I just did it with like 2 insertions of the stress tensor, keep on adding more insertions, and basically constructing the appropriate thing. This is an exercise. It's a tedious one, but it's something that you can systematically do, okay? So they have higher spin currents. And we know that low energy effective theories of gravity do not have higher spin currents. Second, there's a Hagedorn growth of light states. So this is something that was shown back in 2011 by Christoph Keller. And basically the statement is that light states are basically, I'll define them more as we go along, but for the context here, they're states whose conformal dimension is less than C over 12, or if you want, depending on how you measure things, they're light because the conformal dimension will not grow with the central charge of the theory. But these states basically have an exponential growth, okay? And this type of exponential growth is not compatible with a QFT on a curved background, okay? So if you have a quantum field theory on a curved background, the growth is always, this power here is not 1, it's always less than 1. It's basically d minus 1 divided by d, if d is the number of dimensions that your conformal field theory lives in, okay? So this is why also I know that this is not a low energy effective field theory from the point of view of the dual. And then there's a third reason, but this reason is actually related to the first one, so I'm cheating here a little bit. But basically these higher spin currents basically spoil chaos and the out-of-time order correlator. And so this type of correlator will not decay in time, which is something, it's a more fancy kind of criteria that you would put in your low energy theory of gravity, but it's basically a consequence of the first one, okay? So those things already tell me, Alejandra, why are you picking these theories to understand what a holographic CFT is, where clearly it's not a low energy theory of gravity? But okay.
These currents, do they satisfy some known algebra?
Oof, that's an excellent question. It's really tough to figure out.
Perhaps in the limit of large n,
It's even, nobody has been able to work it out. So WN algebras are disgusting. It's not quite Wn or H or W infinity or like the ones that usually appear in higher spin literature, and nobody has given a proper characterization. It's really cumbersome, but you just know that the currents exist. That's quite easy to establish. But yeah, what is the exact nonlinear algebra? It's tough. Yeah, there's certain cases. So for instance, because sometimes the seed theory also provides like currents. So for instance, when you are in the D1, D5 picture, and the seed theory is a free theory, so it's like just 4 bosons and 4 fermions. There are certain limits there that you can take where like people like Gabardiel and Gopakumar have described like have given you some description of what is the expected algebra, but it's very specific, and it's not an easy, it's not fun to do either. But yeah, very good. So those are the differences, and usually, like based on these properties, if you ask, okay, so what is the dual of a symmetric product orbifold? Usually, the dual look like the tensionless limit of a string theory, or it look like a higher spin gravity. Okay, not my low energy theory of gravity that I wanted to start talking about. But this is also again kind of a hand wavy. I can't demonstrate to you like, oh, it will be this. But these are features that we know that appear in tensionless string theory or in a higher spin theory. So it's kind of like, okay, it should go along those lines. But now let's see how they do look like a low energy gravity. So why are they good mimickers of low energy gravity? Okay, so these are properties because I'm interested in how they look like low energy gravity. I will always be, everything that I say here, you do have to have in mind that it's a large N limit of the theory. Okay, so the first property is this factorization of correlation functions. So basically here, I'm looking at operators that we call light, basically operators whose conformal dimension is finite in the limit n going to infinity. And here I'm writing down the formula for what's called a single trace operator. So the number of traces in this context is basically the number of independent sums that you need to symmetrize an operator as you insert it in a copy. Okay? So a single trace operator in this language is basically where you only needed a single sum, and that can be either an untwisted operator where you just have it a single copy of it and then you symmetrize it, or a twisted operator where you use just a single cycle for the twisting. Okay, so basically very similar to what happens in N=4 super Yang-Mills in higher dimensions. What you see there is that correlation functions of single trace operators, basically the connected part of that correlator decays with n in a suitable fashion. Okay, so this is what people call the factorization property of the correlation functions, and symmetric product orbifolds obey it, which is great. Okay, nice property of symmetric product orbifolds. Now, a more non-trivial property related to the phase structure and the entropy. So consider, for instance, the partition function at large n. So if you take the strict n going to infinity limit of the partition function, it basically has this property. When beta is bigger than pi over 2, it goes linearly with beta. When beta is less than pi over 2, it goes like 1 over beta. Beta equal to 2, so here these are modular forms. Beta equal to 2 pi is basically the self-dual point. And from this, basically, you can infer that the density of states grows like the square root of the energy, which is the Cardy formula in a 2D CFT. And these are properties, basically, if you're doing ADS3 gravity, this is what we associated to the Hawking-Page transition, and these answers basically reproduce the area law of the BTC. Okay? So symmetric product orbifolds, from this point of view, if you're just interested in thermal properties of like just the partition function, you would have said, this reproduces the same physics as black hole physics. Okay? Highly non-trivial property that a symmetric product orbifold reproduces. And then again, it's completely independent of what you put there as a seed. The only thing that I'm assuming is that the seed is unitary and it has a gap between the vacuum and the next state, and you will be able to demonstrate this quite generally. Quite impressive for something that was not dual to gravity. Yeah.
This transition in the symmetric product is it by the Hagedorn deconfinement?
Yes, it's a confinement-deconfinement phase transition.
Like in free field theory on S3, the people studied long ago. So the deconfinement transition, Hagedorn goes of states, and then
sure. Yeah, but this is, yes, exactly. It's exactly the same, and in higher dimensions, you would also attribute it from the point of view of the gravity dual to the Hawking-Page transition. But yes, this is a confinement-deconfinement phase transition that happens because you're taking n to infinity. So at any finite value of n, there's not a phase transition. It's only a phase transition when you take the strict n going to infinity limit. But yes, it's the same Witten 98 paper version in a CFT2. Yes. Okay, so that's quite impressive. Symmetric product orbifolds can mimic black hole physics. They can also do more than that. So something that we did very recently this year is that we looked at thermal correlation functions, okay, of single trace operators. So basically 2-point functions on the torus at infinite n. You get this beautiful answer, no matter what the seed theory is. That's the 2-point function that you get on the BTC background. So they don't just like give you like this Cardy-like formula. If you compute basically correlation functions of these light operators, you will get the same answer for the correlation function on the BT set. Okay? And this is basically telling you that you can, if you try to use basically properties of thermal correlation functions as an indicator that you have an emergence of space-time or that you hit a horizon, basically this is telling you you're kind of faking it in a sense. Okay? So these are theories for which, yeah, again, I don't care what you put here. You will always get this as an answer for a single trace, or even more generally, it will be for any light operator. Okay, and there's also quite a bit of universality in certain heavy light operators that correlation functions that we looked at. Okay, so it's quite impressive. These theories really do a really good job at trying to mimic gravity depending on the observable that you look at. And basically, it gives you a lesson of what should we consider a stringent property of a CFT. Okay, so we have basically, in terms of all the universal properties that symmetric product orbifolds satisfy, just as a summary of what I have presented to you so far, I've given you 3 properties that tell you how they mimic really well low energy gravity. So if you would have imposed these as basically holographic conditions, you would have said, oh yes, this is a holographic CFT. Well, no, because there's other conditions that tell you, no, actually, they're not going to be a low energy theory of gravity because of these other criteria. So in this context, you're trying to understand basically that there are some conditions that are necessary. For instance, you would have said that it's necessary that the thermal correlation functions match those of the BTC, but it's not a sufficient condition. Okay, so you can't list this as a condition that will unambiguously tell you, yes, you have a holographic CFT. Okay, so this is where the exercise starts coming in of like, when I list to you properties of what defines a holographic CFT, did you really find something that was just necessary, or did you find something that was sufficient? And a great place where to test it is in symmetric product orbifolds, because you will find that not all of these conditions are stringent enough. So let me see how I'm doing on time. So I have about 15 minutes, 10? Okay. You wanted time for questions as well? Okay. Okay. Okay, very good. So let's move now to the second part of the talk. I'll probably be done less than 15 minutes. So with that, you might say, well, then it looks like every symmetric product orbifold is the same. There's no difference between them. You will get all the same features. What was special, let's say, about D1, D5? Like, why was that like a lamppost to demonstrate it ADS CFT if I just given you a whole slew of properties where I didn't have to say anything about like some deep brain system, some fancy string theory. I was just doing conformal field theory and studying how these things behave at large n. That's all, okay? So let's explore a little bit more then in this context. What does it mean for something to really have this nice properties related to gravity, okay? And so here comes a more sophisticated version of how I want to understand symmetric product orbifolds. And basically, I want to understand their moduli space, and I want to understand if in their moduli space there can be a supergravity point. I'll refine this question a bit more as I go along. But basically, I want to see when a symmetric product orbifold could lead to something that is strongly coupled with a low energy dual, gravity dual, okay? And so I'll basically try to understand what are necessary conditions for this to go about, okay? And I identify which of these symmetric product orbifolds comply with them. Good. So let's draw two circles. So we have basically a space of theories that I'm calling holographic CFTs. This is what I'm trying to characterize and what I'm trying to design. And we know that there has to be various properties, some requirements on them. And on the other side, I have symmetric product orbifolds, which I think I already made a compelling case that they're not holographic, right? We're all convinced that they're not holographic. Yes, the circles do not intersect. Okay. Now, but I have a nail. I'll keep on hammering on it, and I have a hammer. So like, let's keep on this story. Well, they're close. So now I drew them a little bit close together, but not just to kind of be like, well, but maybe there's something I could learn about holographic CFTs by having them a little bit closer together. And the way that I'm going to think about this is in terms of this moduli space. So by moduli space, I basically mean the set of exactly marginal deformations that I can have in a conformal field theory. And basically, the symmetric product orbifold theory, if I'm drawing here question marks because I first have to establish that this cloud exists, but basically, the symmetric product orbifold theory would have been something like a weakly coupled point in this cloud because it was dual to something that it was tensionless. It looked like a free theory a bit. Basically, the copies were not interacting much with each other, so that's why I'm calling it weakly coupled. It looks like floppy. But maybe I can turn on a marginal deformation, so that's what I'm labeling here by some operator that has conformal dimension 1,1, and that turns on some coupling. I turn on this operator with some coupling lambda, and maybe there's another point by turning on this deformation where the theory becomes strongly coupled, and that's my dual that has this low energy description, okay? This is the cloud that we've been taught in the context of the string theory constructions. Oh, there's a very fancy, complicated moduli space, maybe. Yeah, well, we have various indirect evidence that it's there and various checks, but okay, maybe this is what's going on. And so now the question is, when can I really, when is this picture holding, okay? So when is the symmetric product orbifold something that I can deform and that I can connect to something that is strongly coupled, okay? And so what we'll do now is focus on theories with supersymmetry with at least 2,2, because otherwise I don't know how to define the cloud. So I only know how to do it if I have enough supersymmetry to actually establish that the deformations are exactly marginal. Basically then what I'm going to do is try to find evidence for this point by looking at two criteria. So it's quite simple what I'm going to do. First, that the symmetric product orbifold has moduli, okay? That it has deformations, exactly marginal deformations, okay? That's my first criteria, so that at least this cloud makes sense. And then the second is that I'm going to look at quantities that are protected under the cloud. So there are certain quantities that will not depend on the coupling. And so if I compute them here, they should already have the features that I want at the strongly coupled point that should be compatible with gravity. And my favorite quantity in that context is what's called the elliptic genus. It counts a quarter BPS states. And this thing is very important also as well for black hole physics, but it basically has to satisfy, this elliptic genus will have to satisfy various of these sparseness conditions that I'm listing here, okay? Yes?
Does that mean that the correlation function that
Yes, which is very remarkable.
yeah,
That because the operators, like even for protected operators, it's kind of weird. Like its thermal correlation functions are not protected, like generically. So it's really strange that it's there. But yeah, we're very surprised about these results. It also has impact on like how you understand basically microstate geometries and a lot of the fuzzball type program, because it's basically as well indicating that you have all the structure here, regardless of the details. But in any case, we'll look at these two basically properties here that are independent of the coupling that I know from supersymmetry, that are independent of the coupling, and try to establish, will this give me a signal, okay? You might be suspicious based on what already happened to you. It's like, they're all going to be the same, right? Because everything that I've had told you so far holds for all of them. And here's where the surprises come about. So, as I said before, we're only going to consider CFTs that are unitary and compact. So you can try to generalize this for things that have a non-compact spectrum, but it's a bit more tricky. So let me keep my life simple. And again, we're going to consider theories that have at least 2,2, so that I have the confidence of these things being actually protected quantities. It will hold for 4,4 and higher, but yeah, and if you put 0.4, I'll get nervous, but in any case, there might still be things that you can say. Okay, now, out of this circle, actually, so this circle here illustrates all the possible symmetric product orbifold theories that you can do. I want to say first that actually the majority of symmetric product orbifolds will not have a moduli space, and the sense of having exactly marginal deformations. And the elliptic genera basically is going to not comply with what you expected from a holographic sense. So basically the elliptic genera will have this Hagendorn growth, because that was part of the, like all the states. So what I showed you in terms of the phase transition was that if you just computed the partition function, you had a Hagendorn growth. You might be hopeful that the elliptic genera, because you're counting less states, it should grow slower. Most of the time, the majority of the time, it does not. It still has a Hagendorn growth of states. And so from that point of view, it's a protected quantity. Move around how much you want. It's going to be Hagendorn everywhere in this moduli space, if the moduli space exists. Okay? So this is usually what's happening. Okay? So you grab, and we showed this. You can prove it, that most of the time you're not going to get, the elliptic genus is going to be growing like Hagendorn. But there were some nice features, because again, we know that at least D1, D5 things worked. So at least there's one point in this circle that things should be okay. And so we actually found two different types of things that would happen that I'm illustrating here by these circles. And the sizes are a little bit characteristic of what's happening. So there was a small circle that we called type 1 theories, where you do have moduli. There are single trace twisted BPS states that could define my cloud. You don't need the moduli to just be well, the marginal deformation. You don't just need it to be BPS. If you want to have this this gravitational, this strongly coupled point, it's also important that the deformation is single trace, so it has the biggest effect at large n. And it's also good that it's in the twisted sector, so that it really makes the copies interact between each other. Okay. And if you look at the elliptic genera, they basically all have a growth less than Hagendorn, which was great because that's compatible, and that was one of the first checks. Well, not the first, but it was an old check from like '99 of how the elliptic genera growth compared to the supergravity growth, and it has like the growth is much smaller, so it's compatible with a supergravity type growth of states. Okay. So what are the characteristics of this type 1? Well, the central charge of the seed always has to be less or equal than 6. Guess what? The case of D1, D5 on K3, it's equal to 6. So when you were doing string theory, you're just at the edge, which is interesting. If the central charge is bigger than 6, then you're in the red zone automatically. So there's nothing else to discuss. When the central charge is between 1 and 3, our search is completely exhaustive. They're the N equal 2 Virasoro minimal models, and they all fall into this classification here. Between 3 and 6, I don't have a classification of full supersymmetric conformal field theories between 3 and 6, but I can construct many. And we can basically check if they fall into here or don't. Okay, so if you present to me the CFT, our method basically we'll just go through quite quickly in showing this, okay? It's interesting that there's not just, so in the case of D1, D5, there's just a single deformation. Well, there's multiple of them because of supersymmetry, but it's basically just the Ramond ground state that is twisted. And here in these cases, there's more different types of deformations, so that's kind of fun. And there's also some multi-trace deformations that you can have fun with as well that are exactly marginal. Okay, 5 minutes. Great. Now, so that was type 1 here, the small little circle. Then what is this blue circle here? So this is what we call very cleverly type 2. So here, basically, there is moduli, so you can have an exactly marginal deformation that is single trace, twisted, and BPS. However, the elliptic genus still grows Hagedorn-like. So you have a cloud, but you will never have a strongly coupled point. So they will never be holographic in that sense. They will never lead to something that is holographic. It's kind of interesting also from the point of view of this criteria that demanding that you have a moduli space is not stringent enough because you can still not meet all these properties. However, I should say that out of all our searches, if you first demanded that the elliptic genus was sparse, you always found that there was a moduli space associated to it, which you could have thought that there wasn't. But in any case, there's a kind of hierarchy between these two conditions here. But this basically tells you something interesting also, that how the symmetric product orbifold will respond under a deformation will be very different, or there should be significant differences between the type 1 and the type 2 type theories, okay? And this is basically where we are at the moment. So given this, given that, for instance, I have established that within symmetric product orbifolds, they're not all the same. There's some of them that could lead to something holographic, and they're in this little circle here. Would you have told me, this is enough, now we're done, this will lead to a holographic CFT, or what else do I need to do to convince you this thing will have a holographic CFT? Happy to hear what computation we have to do. They're all pretty complicated, the ones that I can think of, so that's why we haven't done much more, but any case. But it will be really nice if this was all I had to impose, and then this was sufficient criteria to lead to something where it had a strongly coupled point. But basically, now that I do have this, and I have candidate CFTs that did not come from a string construction, could you try to figure out what the gravity dual is with this information? So I'll give you all the chiral primaries. I'll tell you all you want to know about quarter BPS states. Is that enough to reconstruct a low energy theory of gravity consistently? I don't know, but they're out there, okay? So defining gravity basically from the CFT. So now conclusions. basically, my big question here, what I was starting with, was which classes of CFTs could capture classical and geometrical properties. I think, again, it's a difficult question, but it's something that now, with all the experience that we have on ADS-CFT and all that we have done, I think we are in the right setup to push this further. And I do think the answer to this is that symmetric product overfolds do teach us quite a lot about what it means to establish the correspondence and how to define it from one side to the other. Where you kind of can use this in two senses. So you can use it in a sense of like determining what things are not really very stringent conditions, because symmetric product overfolds will satisfy them. But then also, what are the more stringent conditions that should basically nail down what the definition is? Okay? And so and I think in this regard, based on the results that I have presented, what we need to understand better is to understand how these theories basically respond under the deformations. So explore the cloud and what these marginal deformations are doing. So with that, I conclude. So thank you. Depends on the person that you ask. I've been frustrated about this. I would like to know if it's true that any symmetric product overfold will have a worldsheet description, or I think it will be more like a worldsheet, but I'm not sure. So I would love to know this. And so for instance, yeah, because maybe, yeah, I would love to know the answer to this. There are some other indications. So this fact that there was this bound on the central charge. So you can ask, why was C not equal to 6 so important in string theory? And the reason why it was so important that the central charge had to be 6 from the point of view of the worldsheet was anomaly cancellation. So if you wanted an anomaly-free string theory, you needed to balance the central charges coming from each part of the ADS3 times S3 times K3, and then that told you, this thing had to have like central charge 6, and then you added everything, and then the total central charge was 0. And so that makes you wonder, given what we're finding now, it's like, okay, is there a better way of like, what is the more general anomaly cancellation type condition? Oh, well, we know what, like, is the central charge of the string of the worldsheet equal to 0, but like, how many ways can you solve that for that condition, given some background? Okay, and I don't know what the answer to that question is. Now, if you don't care about the anomaly and you want to just go crazy and let this thing be anomalous, or cancel the anomaly with something else that you add to the worldsheet, like when you're dealing with something fancy, maybe all of the symmetric product overfolds will go in. So it will depend a little bit on what you meant by having like a dual description. But I think answering that, it's already of value. And depending on different people, because I'm being live streamed and recorded for eternity, I will not say names, but you can find in the zoo of string theorists, people that will tell you everything, and people that will tell you, I don't know. Sorry, I should have had the mic closer to my mouth.
In the case where you say that black hole physics doesn't constrain you too much,
yeah,
it appears that there were all cases where you had also on the gravity side universal aspects. So something like log corrections to the entropy, for example.
Excellent question. The log corrections will tell you yes. So right now I'm looking at properties that are the strict n going to infinity properties of the black hole. But if you add subleading 1/n corrections, you will start seeing that things don't work as well. But yeah. But the issue, like for the 2-point function, and the thing is that there were some papers claiming that the spectral density at n going to infinity was going to be an indicator that the horizon, that you had an emergent geometry based on these type 3 to type 2 transitions of binomial algebras. And basically we're showing, no, that's not a criteria. It's like because you can, like n equal 4 super mills does not satisfy that. If you do correlation functions at n equal 4 super mills at finite temperature, you will not find that they look like a black hole. So that's sorry, at weak coupling. Sorry, at weak like. Yeah, so the things that they're mimicking about the black hole is the strictly n going to infinity. If you do 1 over n corrections, then you will see differences. But still, like it's basically, it's a like you have to start refining, right? And that's also fun because you might have thought that the black hole was just defined by its semi-classical behavior, and no, this is telling you a black hole. Like you have to go into the quantum to really understand this is a proper black hole. So I think the quantum corrections to black hole entropy are super important in this context of understanding what does it mean to have a good UV completion, what does it mean to have a CFT description for that black hole. You can't just rely on the area law to establish that you had a good match. Yeah.
The marginal deformations that you consider are marginal for any n or for large n?
They're marginal for any n. Yes, yes. Like you just care, like they're dependent on the seed. So the seed theory, because you build them out of operators that are in the seed theory and the central charge of the seed. But yeah, we constructed them at finite n, and then you can also take the limit n going to infinity. No, they don't change it. No, they're not. At least the ones that we like. So we had in one of our papers, we had a table with all the deformations listed. Well, you just have to have like n equal to 2 or bigger. So otherwise, yeah. But they do exist for any value of n.
Okay, one last question.
I have a question on the correlation functions, maybe rather naive. So for many CFTs, we can write down the correlation functions in terms of some H-theory object, H-theory partition functions for like HT conforming.
Uh-huh.
Is it possible to adopt such a description for this symmetrical orthoform?
Not that I'm aware of. Yeah, I don't know if a description like that for a symmetric product or before.
Okay, so let's thank Alejandra again. Okay, so our next speaker is Prem Kumar, like from Swansea University, and he's going to tell us about the projections and teleportation operator quenches in CFT.
Thank you very much, and thank you to the organizers for inviting me and giving me the opportunity to speak. at this meeting. So it's a pleasure to be here. It's my first trip to Athens. I will try to do some sightseeing at some point. Okay, so this is a talk based on some work that I've been doing with my collaborator Tim Hollowood in Swansea, and Zsolt Gyongyosi, who's a PhD student there. What I'll be presenting is actually a calculation. So you will see that I will be presenting a very specific calculation in 2D CFT. The motivation for this calculation comes from a series of works and series of ideas that we've been pursuing in the context of black hole evaporation and the information puzzle. But the actual content of the talk that I'm going to give will be essentially a calculation in 2D CFT. That's really what it is. Because the calculation is interesting and there are some puzzles that we don't understand. Okay, so here's the outline of the talk. So I'll give you, to begin with, the basic motivation for why we did this calculation. And the context is the information loss puzzle for black holes, and particularly the idea that somehow information retrieval from black holes is related to the idea of post-selection or projection, an idea which usually comes when we do measurement in quantum mechanics, and that results in a projection onto some state in the Hilbert space of the theory. And then I will talk about describing this idea of projection and post-selection, that's the pointer, in 2D CFTs. So I will promptly move away from gravity and go into the more comfortable setting of 2D CFTs where we can do computations. And in that context, I will discuss the idea of a local quench, which is to create a disturbance, a local disturbance in the CFT in this projected state. And then I will describe a computation of Renyi entropies, entanglement entropies, and in particular Renyi entropies associated to these local excitations that are produced in the CFT. And then we'll compute what I will call the efficiency of teleportation. And we'll see that there is a puzzle that emerges in the limit when you take the n that labels the Renyi entropies and you take it to the limit n goes to 1 in order to compute an entanglement entropy. You get a puzzle which we don't completely understand. We don't know what its resolutions are. And then I will point out some large C observations if I have time, and then summarize. Okay, so the overall bigger motivation is in the context of black hole information, and this idea of post-selection or projection is something that made its way into this subject very early on from a paper by Horowitz and Maldacena, where back in 2003, where they proposed that one possible way in which you can understand information retrieval from a black hole, or the fact that the Hawking process actually is consistent with unitarity, is that in the final at late time in a Cauchy slice that is close to the singularity, there's some kind of projection. There's a boundary condition that projects the quantum state of the system such that the information about the degrees of freedom or the infalling modes behind the horizon gets teleported out to the Hawking radiation. So the idea is that at late times, at a Cauchy slice which approaches the singularity, there's some kind of projection operator which acts on the, so here in this picture what you can see is, to set the stage, A here represents a Hawking mode, a mode of Hawking radiation, which is maximally entangled with a partner P behind the horizon. And V bar represents an infalling mode. So V bar, I use a notation V bar because later on in the CFT, V bar will correspond to a left moving or antichiral excitation, and so that's my notation. So V bar here corresponds to left moving modes, A a Hawking radiation mode, and P its maximally entangled partner behind the horizon. So the idea is that of the final state projection is that towards the end of time, there is a projection such that the projection operator which acts such that it acts on the Hawking partners and the infalling matter the system of the Hawking partners and the infalling matter in such a way that when it acts on the wave function for the semi-classical wave function, this action teleports the information of the infalling modes into the Hawking radiation outside. So it teleports the information of V bar into A, which is the Hawking radiation. Now, this was a nice idea, but there are problems with this proposal. First of all, if such a mechanism actually operated, it would mean that there is instantaneous transformation, instantaneous, what do I write here? Instantaneous or acausal information transfer from the interior to the exterior. And in addition, this projector, we don't know what it has to be, because in particular it has to be extremely fine-tuned in order for 100% efficiency, in order for all the information on the infalling matter to be transmitted outside. This projector has to be something really special for it to achieve 100% efficiency. But the main problem here is that it would be something that violates causality and locality. Now, more recent developments in the context of the information puzzle have actually revived this idea in a more refined form, in a form that's more palatable. And this is basically the idea that as a black hole evaporates, the Hilbert space, the dimension of the Hilbert space associated to the black hole, which is effectively the microscopic Hilbert space, at a particular time, which we call the page time, the dimension of this Hilbert space becomes smaller than the semi-classical Hilbert space, which is actually the Hilbert space of the radiation degrees of freedom. And so if we are trying to understand how information retrieval or unitarity works in the semi-classical picture, we have to recognize the fact that the map from this effective Hilbert space, which is the Hilbert space of the effective theory, semi-classical theory, the map from the effective Hilbert space to the microscopic Hilbert space actually involves a projection. So as the system evolves in time, this map is what we would call a non-isometric map. So it's some unitary transformation followed by a projection. But this is not a drastic projection as in the case of the final state proposal. It's an incremental process. So it's incremental projections, and therefore the idea is that at the semi-classical level, not at the microscopic level, at the semi-classical level, if you want to think about the information recovery from black holes, you have to think of you can think of this as teleportation, but is kind of incremental teleportation as the system evolves. So that's the idea. So that the process of information recovery in Hawking radiation is an incremental projection process. So since we are talking about the semi-classical or the effective description, we are talking about field theory degrees of freedom. So a very natural question then to ask is, can we study this kind of projection and teleportation just within CFT or in field theory? Okay, so that's what we will do. First, let's talk about a couple of things. Quantitatively, how do we want to characterize this teleportation of information? Well, so the most natural thing to do is you look at this infalling mode. We can call that a diary, as is customary in the literature. You throw a diary into the black hole, but you want to maximally entangle this diary with an auxiliary system, which we will call V. So V and V bar are like bell pairs. So that's the way you want to think of them. And then you want to calculate the mutual information in the Hawking radiation and V, the entangled bell pair. If you find that the mutual information is 0, which is what you will find before projection, there's no information of V or V bar in A. Now, after this projection, whatever it is, you should find that if information is starting to get recovered, then you should find that this mutual information should become non-zero. And if the information is completely retrieved, the mutual information should become twice the von Neumann entropy of this diary V that you have thrown in. And that just follows from the definition of the mutual information. So mutual information of A and V is entropy of A, von Neumann entropy of A, plus von Neumann entropy of V minus S A union V. So when projection happens and V bar, or at least portions of V bar, are returned into A, or if all of V bar is returned into the Hawking radiation, then A union V bar, the A union V, Hawking radiation union V, will purify V, and so then you will find that if you compute this, you get twice the von Neumann entropy of the diary. Okay, so that's a very nice way to characterize this. So this is the kind of thing we want to compute. Actually, we compute something slightly different, and I'll tell you why in a minute, because it's visually more appealing. The entropy of the diary is fixed. So in fact, I don't need to compute the mutual information. I just need to compute the difference of SA minus SA union V before and after the projection. This thing is something fixed. Okay, so I'll just remove this and in fact consider this quantity that we call delta S. And this is what we will use to characterize the efficacy of the teleportation. Delta S will be S of A union V, where remember A is the Hawking radiation, V is the diary that we've, or the Bell pair associated with the diary that we've thrown in. And so SA union V minus SA, this is what we'll compute. And so a measure of, this is a good measure of the success of teleportation, because if you think about this schematically, before you do the projection, delta S should be simply the entropy of V alone. And then after the projection, when the information has of V bar has made its way into the Hawking radiation, you should find that this object goes to minus S of V. This is exactly the same information as contained in the mutual information. But the basic idea is for perfect teleportation, this delta S should look like a step function, goes from plus S of V to minus S of V. That's the goal to achieve. Okay, so I want to move completely from all of this to talk about 2D CFT. Okay, so I want to think about 2D CFT, and I want to think about throwing in these kinds of excitations or diaries, and which are like local excitations. So these correspond to naturally some local operator acting on the vacuum state of the CFT, inserted at some space and time point. W and W bar are your left moving and right moving coordinates as usual. W is x minus t, W bar is the left moving coordinate. And I will assume that this operator OW W bar has some decomposition or a chiral decomposition in terms of holomorphic and anti-holomorphic, or chiral and anti-chiral operators. It's quite natural. And where this sum runs from 1 to d. This d here would be what we would call the quantum dimension of this operator, and that would give you the entropy of the diary. So the way you compute the entropy of the diary, imagine that this is like a Bell pair, except you've got d degrees of freedom or d spin states here, and you compute, like for example, the Renyi entropy for that, and you'll find that that's just log of d, log of the d. So that's the so-called quantum dimension of this operator, and that's also the entropy associated to the diary that we are throwing in. Okay? Yeah.
Quantum dimension always an integer?
It doesn't have to be, and those are the cases I think in CFTs where I can't write down this decomposition. So, but I'm going to assume that this decomposition exists because it's visually or conceptually easier to actually do the analysis. If you don't have such a situation, then you'll have to appeal at some point to the transformation of the conformal blocks under various things that you do, but the result is exactly the same. Okay? Does that answer the question? Okay. Okay, so I'm going to consider this quench in a 1 plus 1D CFT and take the insertion of this point and think of computing expectation values in that quenched state. And that means that we'll be interested in computing correlation functions that involve the operator O and the operator O dagger inserted actually at the same space-time point, but that's a serious problem because then the state doesn't have finite energy. And so in order to make this well-defined and smooth, you want to separate these off a little bit into the complex plane. So you give them an I epsilon. You separate them in imaginary time by a small epsilon. And you can in fact do this computation that in such a state you can compute this expectation value of the stress tensor using the standard Bord identities, and you will find an exact expression. If O is a primary, you will find an exact expression for this expectation value. Visually, what you will find is that when you insert this operator, you will create two pulses, one moving to the left, which is our V bar, the diary that's thrown into the black hole, and V is the Bell pair. And these two move at the speed of light, one to the left and one to the right, and they're entangled, maximally entangled, V's and V bars. Okay? Right. Okay, so I've talked about the diary or the quench. My next thing is to talk about projection. How do I talk about projections in a CFT? So so this has been discussed in at least 10 years ago in a series of papers by Rajapur, and they're very interesting papers. I think they're StatMech papers, and the idea is you imagine that you think of your CFT as basically being produced by some discretized spin chain like system, and you take a subset of that spin chain and perform a measurement. For example, measure sigma z, for example, and then you would collapse the spins on those in that subsector into some specific state, let's call it K, and all the other spins are of course left untouched. Now if you think about this, if you think about the initial state before the projection, this is some linear combination of the states along every site. After the projection, it's natural to now see that this state after the projection becomes basically a product of some non-trivial state that's on the remaining sites times some state here which is labeled as K. And basically what you've done by the act of projection is to basically remove these guys from the system. And so a very natural way to think about the act of projection in CFT is to imagine, for example, that you have cut out a slit in the complex plane, if you think about this in Euclidean language. So you cut out a slit and impose some boundary conditions at the lower end of the slit and the upper part of the slit, and that defines for us the ket B and the bra B. So you have a CFT with a slit if you want to study the projected state, and I also want to study a local quench on top of that, which means I have in that slit, in that plane with a slit, I also have insertions of my operators, and I'm now taking care to actually label the chiral and antichiral portions of the insertions separately. So I've got these points here which are light cone coordinates of the right moving or chiral fields, and the left moving light cone coordinates of the barred or the antichiral fields. And the idea is that as time evolves, W bars move to the left, and so the antichiral fields, they enter the projection region, they enter the slit. Yeah, so the antichiral modes enter the slit, and the chiral modes, which are these the right moving operators, they can move from a region where so this region, the blue region, is A, which is basically the system that I'm interested in. So in the context of the black hole evaporation, this A represents essentially the Hawking modes. So the chiral modes can move from a region which is outside A, can move from the region outside A into A, and what we want to see is how the entanglement entropies of the system, of, for example, the Hawking radiation and this auxiliary mode V, how they vary as a function of time or as we perform the projection. So here's the projection operator schematically, and what we want to compute is this efficacy or the measure of how efficient the teleportation is. So this quantity that I call delta S in the projected state. And we want to compute this as a function of W bar, because W bar is the coordinate of the antichiral modes, and we want to see what happens as you move W bar from outside the projection slit into the projection slit, and how these measures of entanglement change. So the difference that we want to compute is in the entropies of A union V as a function of W bar, and the entropy of A as a function of W bar. So A union V is what you get when the chiral modes are sitting inside V, which means that these points are there. The chiral points are sitting there. And S of A is when the chiral modes are sitting outside A, and so don't include, so V sits outside A, and so you just have the entanglement entropy of A. So I want to compute this difference, S of A union V minus S of A. Okay, so an important point here is that the projection operator does not actually in general commute with the Hamiltonian. And you might imagine that that is the case because if you create a split in the CFT, you know that there will be transients, and that state is not going to be an eigenstate of the Hamiltonian. So what we are going to do, rather than looking at the time evolution of the entire system, we are going to think about the positions of these points, the chiral and antichiral points, as basically parametrizing a one-parameter family of states, and we want to compute the entanglement entropies of interest, in particular this delta S, as a function of this one-parameter family. Okay, and we want to see what the effect of the projection is. Now, if you want this boundary state B to preserve some conformal symmetry, then it's basically a Cardy state. And if you assume that, we can map this W plane with a slit into a half plane with a boundary. So you do a coordinate transformation, in particular W equals zeta squared, and you can open out the slit into the half plane. So essentially what you have done by introducing a slit in your CFT is allowed yourself to map it to conformal field theory with a boundary, with conformal boundary conditions, which means that you are in BCFT. And so in this BCFT, we are looking at a local quench with these chiral positions of these chiral modes, which are these V's. And then the boundary conformal field theory, correlation functions in boundary conformal field theory are in one-to-one correspondence with correlation functions of chiral CFT on the plane. So you can insert your antichiral modes in the image region. So you can think of this boundary as basically implementing a kind of image condition, and you can map all correlation functions in boundary conformal field theory to chiral correlators on the plane. And so you've got this situation where when you look at the antichiral modes moving into the projection slit, that corresponds to the positions, the corresponding positions of those operators moving up and down along the imaginary axis up to infinity. So the projection is when the antichiral points hit the boundary from the left and move off to infinity. And the chiral points, they can be either in A or not in A. So those are the two situations. And we now want to compute the Renyi entropy of this configuration with these operators inserted. To compute the Renyi entropies, you do the replica trick, which means that you have to compute now not just a two-point correlation, but you have to compute, you have to replicate the system along with a boundary, and the system has to be n copies of the system which are joined along this interval A, and that means you have an n-fold copy of the CFT, and you have a 2n point correlation function to compute. And if you compute that 2n point correlation function, take its log, then you get the required quantities that we need in order to measure the efficacy of this teleportation process. Okay, so here's some technical stuff. There are n pairs of chiral insertions in this picture, and I label these n pairs by W's these W2J minus 1 and W2J, J going from 1 to n. N pairs of antichiral insertions labeled by the Bard guys. And the main point in this calculation is that whenever 2 points are close to each other, two of these coordinates are close to each other, you invoke the OPE rule between the chiral fields in the decomposition or the antichiral ones. And the OPE rule basically is this: if you have some VA contracted with some other VA at positions omega 2j minus 1 and omega 2k, and if these two are close, then the result is basically given by 1 over epsilon to the delta, where delta is the conformal dimension, and a Kronecker delta of these two indices. That's basically the only thing that's needed. Okay, so here's what happens when you study this system. So let's look at this. This is the case when this is a picture drawn in this covering space. So when you take the when you do the replica trick, you can use this map z to the n equals this thing to uniformize this multi-sheeted Riemann surface and take the whole system into the complex plane. So in this picture, what you see is the mod z equals one circle, and the mod z equals one circle is actually the boundary, which is the same as the projection slit. So that's the boundary of the BCFT, but also the projection slit. The coordinates zi and z bar I are basically the coordinates of the antichiral operators. And you can see that this is for the n equals 3 replica calculations. So you can see there's z1 bar, z2 bar, z3 bar, z4 bar, and z5 bar, z6 bar. So when the operators are yet to hit, have not yet hit the projection slit, the antichiral operators, you can see that they are close to each other according to this. Z1 bar close to Z2 bar, Z3 bar close to Z4 bar, and Z5 bar close to Z6 bar. And when they hit the projection, you can see that there is a motion of these operators until actually you see that Z6 goes to Z3, Z4 goes to Z1. This kind of a permutation action. And a similar thing happens for the chiral modes. So when the chiral modes enter A, there is a permutation action on these pairwise contractions of the chiral operators. When the antichiral modes enter the projection slit, there is a different permutation action on these pairwise contractions of the antichiral operators. And you can now compute the correlator, the Renyi entropy, which gives the Renyi entropy. In particular, it gives you what's called the Renyi excess, the effect due to putting the quench operators. And you find that it's actually purely combinatorial result. And the result is given by log dimension, this quantum dimension, times curly d of pi and sigma, where curly d of pi and sigma denotes what's called the Cayley distance, which is the minimum number of pairwise swaps that you have to do in order to relate two permutation group elements. Okay, so when the dust settles, this is what you find. So before the projection happens, when you compute the Renyi entropy of A, remember A is like the proxy for Hawking modes. So this is A, and that means that before the projection, both the chiral and antichiral V and V bar are both sitting outside A. So the entropy here is basically 0. There's no entropy effect. After the projection, which means the mode V is still not inside A, right? It's not inside A. But after the projection acts on the antichiral mode, the diary, you see that the entropy of the region A grows by log D, which actually tells you that as the antichiral mode enters the projection slit, somehow the entanglement entropy of region A goes up by log D. So there is teleportation happening. But then you look at A union V. What happens when you put the chiral operator inside the radiation, inside A? Before projection, if V sits inside A and V bar sits outside A, then the entropy of A union V is log D, because V and V bar are maximally entangled. V bar sits outside A, V sits inside A, so it's log D. But after projection, when you look at this Cayley distance business, what you find is this funny result, that the entanglement entropy of A union V, the Renyi entropy actually, is given by n minus 2 over n minus 1 times log D for n even, and is equal to log D for n odd. So completely non-uniform behavior in n, and completely different for even and odd. So if you look at the Renyi excess and compute this efficacy of teleportation, what you find is instead of getting for ideal teleportation, when in the beginning I flashed this slide where this needed to go to from log D to minus log D. So what you see for the Renyi entropies labeled by n is that log D goes to log D over 1 minus n. So if n is 2, for the second Renyi entropy, it looks like you have kind of perfect teleportation. But for all other Renyi entropies, it's imperfect, and that's for n even. For n odd, completely different, log D goes to 0 for any n. So this is distinct from what we would expect for a scenario where there's perfect teleportation. This means that efficacy of teleportation is not 100% for Cardi states. And what's particularly surprising is that the dependence on n is not uniform. And in particular, this is a, well, here I just pointed out that you can do this calculation pretty much exactly, or as exactly as you want analytically, for the free boson system, where you can take this insertion operator to be a sum of exponentials, and this operator has quantum dimension 2, and you can actually show the exact expression, compute the correlator, and show that it interpolates between log 2 to minus log 2 for the second Renyi entropy, but for the higher Renyi entropies, you don't get perfect teleportation. Okay, how much time do I have? Okay, I'm almost done. So here's our attempt to try and see how you can compute the entanglement entropy. To compute the entanglement entropy, you have to compute the Renyi entropies and analytically continue to 1. Now that looks very difficult to do, given that you have such a non-uniform dependence on n. So we try to make use of this approach, which was suggested in a paper by Doker, Dong, and Wu in 2021. And basically what they point out is if you know all the Renyi entropies of a system, then you can form this particular generating functional, e to the minus n Sn plus 1 minus 1 times z to the n over n, sum over n from 1 to infinity. This generating functional, if you look at it closely and recognize that Renyi entropies are just given by traces of powers of the density matrix, this can be written in operator form as minus trace rho log 1 minus z rho over 1 minus z. And this means that if you know all the Renyi entropies for all n, you can compute this sum and compute g of z. And then if you want to extract the entanglement entropy, which is minus trace rho log rho, you take the limit z going to minus infinity of this sum. It's a nice trick, but you have to assume that in z going to minus infinity, there are no singularities or branch points. Okay. Yeah.
Naively probably, but why don't you take n equals to 1 limit from the odd?
Or just looking at the odd ones. I mean, that leaves open the question of what you do with the even ones. Because if you just, so yeah, there are different options you can take. If you took the odd one, you know the result is just log d. It's not entirely clear whether that's the right prescription to use. Also, what's not clear is whether computing Renyi entropies at integer n's versus maybe you compute them and maybe they have nothing to do with the von Neumann entropy. And the von Neumann entropy has to actually be computed in the neighborhood of n equals 1. So that could also be the case. So we implemented this procedure, and what you find is that this generating functional g of z for the choice of for the values of Sn plus 1 we get gives you a closed analytical form. The problem is that this expression has branch points along the negative as z-axis, which means that if you want to do the Docker et al. Trick of taking z to minus infinity, you have to find ways of actually avoiding the branch points or choose some prescription, and that's ambiguous. So the n goes to 1 limit is ambiguous, but if you unjustifiably ignore IPIs that come out because there's logs of unwanted, then you find that this, if you compute the mutual information, it gives you precisely log d, but there's imaginary parts that I have thrown away, but it's a puzzle. Don't really understand how to take the n goes to 1 limit. Okay, so here's some observations on large C, because one can compute these, one can do these calculations also in the large C limit. In large C, you use the fact that the correlation function that we are interested in computing can be viewed as a 3-point correlation function in the presence of a twist operator. The twist operator is the one that creates the branch point in your replica calculation. So it's a 3-point function of a twist operator in the projected state. But then that is a 3-point function in BCFT after you do the conformal map. So it's really secretly a 6-point function, 6-point chiral correlator on the plane. So if you take n to be an integer in the large C limit, the twist operators, or the holomorphic and anti-holomorphic parts, or chiral and anti-chiral parts of the twist operators, they are heavy operators. This is actually opposite to what people do when you're computing entanglement entropy, where the twist operators become light fields because you're taking the n goes to 1 limit. Here the twist operators are heavy, and those other fields have to be viewed as light fields. You can compute the correlator of 2 heavies and 4 lights, and you can compute this efficacy delta S, and you find that actually it does start off positive and then decrease, but it decreases without bound, which is actually one of these characteristics of the large C limit, that the large C limit does not actually see the quantum dimensions of the operators that you are doing the quench by. That's just one of those characteristics of large C, that in the large C limit effectively is like taking the quantum dimension to infinity. So these things never saturate. Okay, so I've got to the summary. So we've investigated teleportation in CFT with a projector onto the Cardy state by mapping to boundary conformal field theory, and we get universal results for the quench, for the Renyi entropies in the presence of quench post projection. What we have seen is that the efficiency of teleportation is less than 100% for Cardy-like states, and there is an even-odd puzzle, and the n goes to 1 limit is clearly ambiguous. There's lots of interesting future questions, not all of which are technically easy to access. For example, understanding the dynamical evolution of the system, the time evolution of the system after imposing this projection, using holography to understand these setups, understanding this kind of SYK information retrieval kind of question in the context of SYK models. Some of this work, especially in the context of holography, has already been done by these guys, the collaborations with Takayanagi et al. So that's all I have to say. Thank you very much for your attention.
Ignoring the branch point.
That's true.
So it seems like
You
it really
might
wants to
suggest
be
that not exactly time dependent. As I was trying to say, what we are thinking about here is taking these quench operators and inserting them at different points, different Lycone coordinates, and studying the entanglement entropy of that state. So if you took any one of these states, like a quench at a particular W and W bar, that would form an initial state for subsequent time evolution. What we are looking at is basically one parameter family of states and looking at the entanglement structure of them as a function of this parameter. So it's not strictly speaking time evolution. If the projection operator had commuted with the Hamiltonian, which it does not, then this would be time evolution.
You know, because in the usual quench business,
Yeah.
there is typical time independence.
Yeah, but you see there,
Here does not appear at all.
well, that time dependence, the time dependence you're talking about in the quench correlation functions, yes, I mean, it's there, but it's a function of this W and W bar. So, for instance, if you, I don't know exactly which time dependence you're referring to, but for instance,
log T for local quench.
for local quench, log T,
Log
in the large C limit, that happens in the large C limit, and indeed, these things grow away logarithmically. That you can see analytically.
And then I have another question. The dependence on the boundary state that you introduced
Yeah.
disappear in your final result or subliminal?
No, because these are calculations. We have assumed here that the boundary conditions are conformal.
Yes.
That's what allows us to compute these correlators. So we have made a very specific choice of the boundary state. If we studied more complicated boundary states, yeah, the calculation would be very different and probably more
Ναι, 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 έχω, ναι. Ναι. Μάλιστα.
Γιατί άλλοι διαφέρουν.
Ναι, ναι, όχι, αυτό δεν είναι. Επίσης, ευχαριστώ πολύ. Γεια σας.
Yeah, no. Yeah.
Sorry, what?
I just sent.
Yeah, I just got it. Yeah, I'll just upload it now and then.
I sent just a minute ago. I sent another one.
I got one email. You sent another one?
Yeah.
Okay.
Right, sorry.
I see. Okay, so I should remove the first one, right?
Yeah.
Just the second one.
Just the second one.
All right. Okay. Sure. No problem. Yes, sure.
Is there a bathroom?
There is. Yes. Sorry. As you go out, on the left there is these panels, just behind the panels.
depends on you.
Ah, I see. There is a choice, but the microphone is for YouTube or over the room.
In any case, I will leave also this open,
Okay.
so it's up to you.
Okay.
But I think it's better for YouTube the microphone. But I don't know if it's convenient for you. So in case that you would like to stand close to the podium, you may use this one. As you would like.
Okay. Yeah. I was just asking which. Is it either mic? And Kostas was saying either mic, and then.
Well, you can in principle use this, but I mean you have to keep.
Yeah. Okay.
Here.
Maybe this is easier.
Whichever
Okay.
you want. Yeah. So, but.
That's fine. Yeah, close enough. Just so something. All right. Okay, great. Thank you.
Okay, I believe that we can start. So it's a pleasure to have Ben Hoare, who's going to talk about integral models from holomorphic theories. Thank you, Ben.
Thank you, Kostas. And yeah, I'd like to start by thanking the organisers for the invitation to speak here. It's my first time in Athens outside the airport. It's a great pleasure. So today what I want to talk about is some ongoing, well, some work with three excellent students who are either just finishing or have just finished, and a collaborator of mine, Dan Thompson at Swansea, and also some ongoing work with Lewis Cole. And the goal of this work is really to understand the integral models that we get from holomorphic theories, as opposed to sort of the more traditional integral models that we may be familiar with. And I'll introduce all these terms. So I'm just going to flash this. There are many reasons why integral systems are interesting in mathematical physics. I've listed some here. There are more. What's been quite exciting over the last couple of decades is that, or last couple of decades, is that the landscape of 2D integral models has continued to grow. So typically this used to be done following an approach of direct construction. This can be very challenging, trying to find a lax connection for a given model. But more recently there have been sort of more systematic approaches, for example affine-Godin models or higher dimensional gauge theories. And also people have been using more general guiding principles such as dualities and deformations. And I should say that all these frameworks are closely connected. So today what I want to focus on is this third one in the list, this higher dimensional gauge theory story. So two approaches that, well, have been around various lengths of time are 4D Chern-Simons and 4D anti-self-dual Yang-Mills. So the idea of 4D Chern-Simons is to consider a gauge theory which has a Chern-Simons 3 form and an omega, which I'll introduce properly later. And you consider this theory on CP1 times R2, and you introduce some defects on CP1, and it localizes on these defects, this theory, to give 2D integral models. The other approach is 4D anti-self-dual Yang-Mills, and this has actually been around a lot longer. And the idea is to consider solutions of anti-self-dual solutions of the Yang-Mills equations, which can be characterized in this way. There are different ways of characterizing it. And what you find is if you reduce this in a sense of symmetry reduction or dimensional reduction along 2 dimensions, you end up finding 2D IFTs. So Costello proposed and Bittelson and Skinner kind of formalized that you can sort of combine these two approaches into a sort of into a shape which, if you squint, is a bit like a diamond, in the following way. So you have here 4D Chern-Simons. If you localize this, you get some 2D IFT. If you consider this 4D IFT is meant to be anti-self-dual Yang-Mills. If you reduce that, you get to a 2D IFT, and you can sort of embed both of these inside 6D holomorphic Chern-Simons, which I'll introduce in a second. And if you reduce 6D holomorphic Chern Simons, you land on 4D Chern Simons, and if you localize, you directly get to your 4D IFT. So this was proposed by Costello, and a few years back, Bittleson and Skinner worked this out, this sort of diamond out for one particular example or a few examples, and showed that indeed such a structure can work. So this is the action of 6D holomorphic Chern Simons. It's not super important the detail. Again, we have a Chern Simons 3 form, but now it just depends on the 0-1 component of a 6D gauge field. Omega is a 3 form. Again, I'll introduce that properly later. The action is now on twistor space, which in some sense you can just think of as CP1 times R4, but there are important features of twistor space which I'll come back to later, but for now we can just think of it as CP1 times R4, and if you localize on CP1 you get the 4D IFTs living on R4, and if you reduce along 2 dimensions in the R4 you get the 4D Chern Simons on CP1 times R2. And actually you can also reduce along 1 dimension to a 5D Chern Simons theory. So that sort of motivates a slight refinement of the diagram where you also get a sort of 5D Chern Simons sitting in the middle here. Good. So I just want to make a few comments on this construction. So the 4D Chern Simons and 5D Chern Simons are mixed. And what I mean by that is that they're holomorphic topological. So for example, the 4D Chern Simons is holomorphic in the CP1, but it's topological on the R2. Similarly for 5D Chern Simons. The 6D Chern Simons is a sort of fully holomorphic theory. So you can imagine that you're starting from 4D Chern Simons and you're sort of complexifying dimensions and turning topological dimensions into holomorphic directions one by one until you reach 6D holomorphic Chern Simons. To find non-trivial 4D IFTs from 6D holomorphic Chern Simons, it's important that we're on twistor space, and in particular, this is what gives us the complex structure. So the complex structure on R4 depends on where we sit on CP1. So as we move around R4, the complex structure, as we move around CP1, the complex structure on R4 is changing. If you just use the details of that are not too important, but if you just use the trivial complex structure, then you would basically just end up with complexified 2D IFTs, which we don't want. So we want something a bit more complicated than that, something where, so these complexified 2D IFTs would only have derivatives in 2 directions. We want to have derivatives in all 4 directions of our R4, and for that we need this more complicated complex structure. And similar statements also hold for the 5D Chern Simons and 3D IFTs. So this dimensional reduction story, it sort of goes right through the integrability, classical integrability structure. So the equations of motion of the 2D IFTs are governed by a Lax connection, 3D IFTs by the Bogomolny equation, and 4D IFTs by anti-Self-Joule-Yang-Mills. And these are all defined in terms of some spectral parameter defendant 1 form. These are just the notation I'm going to use throughout the talk for various things. And these are reductions of each other. So you can go from the anti-Self-Joule-Yang-Mills connection to connection satisfying the Bogomolny equation to a Lax connection. So, good. So that's one approach, in some sense, to going up in dimensions. So starting from 4D Chern Simons, complexifying in inverted commas 2 of the dimensions, and considering 6D holomorphic Chern Simons. There is actually an alternative proposal for constructing 3D IFTs, and in principle this can be generalized to higher dimensional integrable field theories. And I'm not going to go into details of this model, but for the purpose of this talk, I'm just going to say it's a mixed 5D 2 Chern Simons theory. So it's based on a Lie 2 algebra, and it has both a 1 form and a 2 form gauge field as its field content. So as I say, the details are not super important, but the presence of the 2 form gauge field is interesting. In particular, if we think about conserved charges in higher dimensions and generalized symmetries, it's natural to expect that integrability in higher dimensions would require higher form symmetries or generalized symmetries, and the extended objects which would couple to higher form gauge fields would be important for this. This is sort of schematic, very schematic, and you can think about the sort of tetrahedron equation in quantum 3D integrable field theories and also membranes as kind of examples of this. So the goal of this talk is really to understand what the relationship is between these two different proposals. So one proposal for going higher in higher dimensions is to consider this sort of complexification, and one is this categorification. And the motivation for this comes from, in particular, this 5D Chern-Simons and 5D 2 Chern-Simons, and both Bittelson and Skinner, and then Schenkel and Vicedo considered these respectively, and both of them seem to get what's called the Ward models. The Ward model, again, details are not important, but it's a 3D generalization of the principal chiral model. It's meant to be integrable. There are nice scattering properties and has kind of many of the usual features of integrability. So both seem to give the Ward model in a sense, and our question, what we want to understand is how is this related? How are they related? Another way of thinking about this is, so I was arguing up here that the two-form gauge field is important for symmetries, and in principle for integrability. But the 5D Chern-Simons and 6D holomorphic Chern-Simons, they still only have a one-form gauge field. So the question you might ask is, do the 3D and 4D IFTs constructed from these have the conserved charges that you would expect to be the hallmark of integrability? So I'm not going to work with 5D Chern-Simons. They are, well, 5D Chern-Simons and its higher categorical generalizations are tractable. You can work with them, but they are significantly more complicated than 4D Chern-Simons. So actually what we're going to do is we're going to simplify the story. We're going to go in the other direction. So it turns out that you can also construct 1D integrable field theories from a 3D mixed BF theory. So this is something that Vicedo and Winston were working out. And this 3D BF theory also has a holomorphic counterpart, which is known as 4D holomorphic BF. So our approach is going to be to look in more detail, take this 4D holomorphic BF theory more seriously, and look at the 2D IFTs that we get from it, and try to compare these to the 2D IFTs we get from 4D Chern-Simons. So I should say that this idea that this diamond might exist and that you can get 2D IFTs from 4D holomorphic BF is not new. There are examples in the literature, but they're kind of sporadic. So I have a diagram. So hopefully, I appreciate I've introduced many, many concepts very, very fast. Hopefully this gives a sort of sketch of what we're trying to do. So for those who are used to familiar 2D IFTs with a lax connection, that's basically sitting here. That's this 2D IFT. They come from 4D Chern-Simons. This diamond here, this pair of diamonds here, is the one I introduced first, where we lift, we complexify, and we go up to 6D holomorphic Chern-Simons, giving 4D integrable field theories. And these are the ones that are characterized by anti-self Julian-Mills. In principle, we can jump up here to 5D 2 Chern-Simons and 3D IFTs. And we might ask how this pair of theories is related to this pair of theories here. But instead, what we're going to do is we're going to jump down here to 3D BF and 4D holomorphic BF and ask how this pair of theories, so 4D holomorphic BF and the 2D IFTs that you find from it, are related to 4D Chern-Simons and the 2D IFTs that come from that. Good. before I continue, are there any questions about the kind of the goal of the talk, or everyone happy? So this is going to be the plan of the talk. I'm going to spend a little bit of time discussing integrable field theories from 6D holomorphic Chern-Simons. That's this diamond up here. I'm not going to mention 5D again. I'm then going to move on to this diamond down here, so the 4D holomorphic BF, and the 2D IFTs you get from that. And then I'll try and sketch the relation between these two constructions. And then I'll list a bunch of open questions. Okay, good. So let me just start with what was known before we started to look at this. So Bittleton and Skinner, they constructed this diamond that I'm going to sort of keep track of down in this bottom right-hand corner, essentially for the 2D IFT being the principal chiral model plus the Wess-Zumino term. And what I'm going to mainly do is go through their construction in a little bit more detail to sort of give everyone a flavor of what's going on. Early attempts to generalize this were complicated by the fact that it was unclear how to lift the boundary conditions from 4D Chern-Simons up to 6D holomorphic Chern-Simons, and it was also unclear what gauge symmetries to expect in the 2D and 4D IFTs. So we started to look at this question, and we managed to construct the diagram for a particular current-current deformation of the Wess-Zumino-Witten CFT, which is also known as the lambda deformation of Svetsos. And we also looked at certain gaugings of the principal chiral model plus Wess-Zumino term. So, okay, it's still 2 more examples, but I think by now we kind of have a pretty systematic understanding of how you would go about doing this in general. Good, so seeing as this is a low dimensional conference, I'm going to start at the bottom of this diagram. So what I've written here is the action of the principal chiral model plus Wess-Zumino term. Hopefully it's relatively familiar to people. G here is a group valued field. We're in 2 dimensions on R2. J is the Marat-Cartan 1 form. This is the usual kinetic term, which if this second term wasn't here, would just define the principal chiral model. And then we also have the usual 3 form, the Wess-Zumino term. K is quantized, it's the level, and H is the sigma model coupling. So when H is equal to 1, this is just Wess-Zumino-Witten. And if you take H equals 0 in a careful way, you can recover the PCM. So we can compute the equations of motion of this model varying G, and what you find is the following equation. In particular, this is just the conservation equation for this particular current here, K. So D star K is just tells you that this is equal to 0. And actually, this, if you compute the curvature of K, you also find that on the equations of motion, it vanishes, and it's a sort of standard procedure in 2D integrable field theories that if you have a flat conserved current, then you can construct a lax connection. So this is what I've written here. So L is defined in terms of this flat conserved current K, and zeta, so zeta is a spectral parameter, it's complex valued, and the flatness of L for all zeta is equivalent to the equations of motion. And this is a sort of slightly more technical detail, but the Poisson bracket of L, the spatial component of L with itself, takes a particular form known as Maillet form, and what this implies, what's important, is that this implies that we have conserved charges in an involution, and we have the usual tower of integrable conserved charges that we would like. So, yeah, this is the theory that we're going to be looking at that sits down in the bottom left, and we're going to look at, first we're going to look at this left-hand leg, how this kind of originates from 4D Chern-Simons. So I already briefly introduced the 4D Chern-Simons action. Let me introduce it in a bit more detail. So A here is a G-valued one form on CP1 times R2. So we extend our space-time R2 by the complex projective space. And we build the Chern-Simons one form for that space. And then we wedge that, because that's the 3 form, we have a 4-dimensional space, we wedge that against omega, which is some specified meromorphic 1 form on CP1. So it's meromorphic, so it's allowed to have poles, and they will be important. To define the theory, there's by now a very systematic procedure that you can follow. You first need to specify omega, so your distribution of poles and zeros. You can also change CP1, but for now to some other Riemann surface. You also then need to specify some data. In particular, we think of the poles of omega as boundaries. So we need to specify boundary conditions at these boundaries such that the boundary variation vanishes. And omega can also have zeros. And at those zeros, we can still have finiteness of the action if A has poles at those zeros. So, but those need to be finely tuned so as the poles in A don't overwhelm the zeros in omega. So, and we do this by imposing certain regularity conditions. The details are not particularly important, but this is the data that we need to define a theory. So omega, a particular one form, some boundary conditions at the poles, and regularity conditions for the connection A. The boundary conditions break the gauge symmetry, and what we then find is that there's a effective 2D IFT that lives on the boundary as a result of this gauge symmetry breaking, and this is just the edge mode theory. So these are, you introduce some bulk fields, and the edge modes that live on the boundary give this 2D IFT. And I should say that depending on how mathematical you are, you have a range of approaches available to you. So for the principal chiral model plus Wess-Zumino term, this is the particular one form that we use. So it has 2 zeros at plus and minus 1. So zeta equals plus and minus 1. And we also have a double pole at zeta equals h, which I just represent by this random point here. And finally, we have a double pole at infinity, which you need to go to 1 over zeta to send zeta to 1 over zeta to see. So I'm not using zeta accidentally. Zeta is here the complex coordinate on CP1, but it will also become our spectral parameter. So I should note that here I've done a little bit of fixing, so using the SL2C on CP1. So I've just chosen to put my zeros at plus minus 1 and 1 double pole at infinity as a matter of convenience. But you can always fix 3 of your points as usual. And then the remaining degree of freedom, or the remaining degree of freedom, is the position of the double pole on the finite plane. So in this talk, pretty much everything we will consider are Dirichlet boundary conditions. So we can just basically say that the R2 part of the gauge field A vanishes at both double poles. We then define, or we redefine A in terms of G hat and L in this way. So basically the zeta bar component of L is chosen to vanish and is completely absorbed into this G hat field. So here G hat is a group valued field evaluated on the whole R2 times CP1. I'm not going to crank the handle today, but you can then partially solve the bulk equations of motion subject to the boundary and regularity conditions, and you find that G hat contains a bunch of edge modes that become the fields of your 2D IFT, and L is then the lax connection of your 2D IFT. that depends on L. So there are a number of very clear papers where this procedure is described. And then you basically substitute this back into the 4D Chern-Simons action, and you find the 2D action of the PCM plus Wess-Zumino term. And as you want, the equations of motion of the 2D IFT are equivalent to the flatness of the Lax connection. Okay. So let me jump over that. So we can now jump up in dimension to 6D holomorphic Chern-Simons. Not here. I'm just considering on R2. Yeah. That's an interesting question. I don't. There has been. There has been some work on that. I think maybe even Bittelson and Skinner had a paper on looking boundaries in 4D. I'm not an expert exactly how that works, but it's an interesting question. Yeah, I think they looked at like K matrices instead of R matrices appearing, but yeah, I don't remember the details. Okay, great. So this is 6D holomorphic Chern-Simons. It's defined over twistor space. Here, omega is some specified. Now it's a 3 form. In particular, it's a meromorphic 3-0 form. And a bar is a 0-1 form on PT. So details are not super important, but this has a complex structure, and this splitting is with respect to this complex structure on twistor space. So so many of this is basically a copy of what has already come. We define the theory by specifying omega. This should be capital omega here, boundary conditions at the poles, and regularity conditions for the gauge field. The boundary conditions break the gauge symmetry, and the 4D IFT is the edge mode that lives on this boundary. So the mechanics is very, very similar. This is the particular meromorphic 3-0 form that we consider. Pi, I'm now using homogeneous coordinates on CP1. So pi is identified with itself up to a scaling. XAA dot are my coordinates on 4D space-time. So we can introduce a particular basis of coordinates on the 4D space-time, Z, W, Z bar, and W bar. And if we then reduce along Z and Z bar, we find that we go from 6D holomorphic Chern-Simons to 4D Chern-Simons. So this is just a sketch of how this works. If we basically take omega and we contract with the direction, the vector fields dz and dz bar, and rewrite homogeneous coordinates in terms of inhomogeneous coordinates in this way, it's a familiar way, what you find is that a one form omega that is exactly the one form that we had that we used for 4D Chern-Simons. So that corresponds to going this way around the diamond. It's also possible to go the other way around the diamond, and in this case we find a 4D IFT in the middle. So again, we take Dirichlet boundary conditions, we introduce a bulk G-valued field such that this A bar of zeta bar, this curly A bar of zeta bar is equal to 0. We substitute this back into 6D holomorphic Chern-Simons, and we find the action of a 4D IFT. There is an analog of the Lax equation, which is basically this equation here, which is equivalent to 4D anti-self Joule Yang-Mills. So this is the particular 4D IFT that we find. It's the theory over R4. It looks very similar to Wess-Zumino-Witten. J is again a Markov-Cartan form for a G-valued field. omega alpha beta here is a specific 2 form that depends on these on spinors alpha and beta, which parameterize the positions of the poles, and this is explicit formula here. The main point I want to make here is this model does not have SO4 Euclidean symmetry, or in Lorentzian signature SO13. That's broken by the presence of this omega alpha beta. So yeah, this is just a caveat to say that when I'm talking about these higher dimensional integral field theories, I'm not necessarily talking about Lorentz invariant field theories or Euclidean invariant theories. We're in a sort of slightly more general setting. I don't know. It may be related, but I don't know. So yeah, just to finish off this example, you can compute the equations of motion, and what you find is that they're equivalent to the anti-Self-Julian-Mills equations for this particular connection here, defined in terms of G. And just as for 4D Chern-Simons, you can find this directly from 6D holomorphic Chern-Simons. So my final comment before I move on to 4D holomorphic BF is just a general. This is more sort of a general comment about how to generalize this whole construction. So, in particular, we can think of dualities. We can understand dualities and deformations in terms of these one form and this one form omega, or the 3-0 form capital omega. So, for example, dualities can be understood as choosing different boundary conditions at different for the same configuration of poles, whereas deformations could be understood, for example, as splitting a double pole into 2 simple poles. And this is where a lot of the subtlety lies when you try to generalize this 4D Chern-Simons to 2D IFT into this full diamond. In particular, many of the boundary conditions that you want to consider for 4D Chern-Simons don't easily lift up to 6D holomorphic Chern-Simons, and you need to consider wider classes of boundary conditions. Okay, good. So that's my summary of this diamond here, starting from 6D holomorphic Chern-Simons. Are there any questions at this point before I move on to holomorphic BF? So the idea is very similar here, and here I'm not actually going to describe the full diamond. I'm just going to focus on this particular right-hand side. So 4D holomorphic BF to 2D IFTs. So this is the action of holomorphic BF. So it's defined on now CP1 times R2. This looks like the same thing that 4D Chern-Simons is defined on, but now we want to consider this as a holomorphic theory. So omega is now a meromorphic 2-0 form with respect to some non-trivial complex structure on this CP1 times R2. A bar is a G-valued 0-1 form, and B is a G-valued scalar that just imposes that A bar is flat. And again, the story goes the same way. To define the theory, we specify omega, the boundary conditions are the poles of, again, capital omega, and we that ensure the boundary variation vanishes, and we impose regularity conditions for A bar and B, actually, and B. The boundary conditions break the gauge symmetry, and the 2D IFT is the edge mode theory that lives on the boundary. So the mechanics is, again, the same. The example I'm going to discuss is this particular 2-0 form. So I'm using, again, the same notation in terms of the homogeneous coordinates on CP1. The important thing to notice is that omega has 3 simple poles. So there's a pole at pi equals alpha, a pole at pi equals alpha tilde, and a pole at pi equals beta. And we're, again, just going to take Dirichlet boundary conditions at each of those poles. And then following a similar procedure to 4D Chern-Simons and 6D holomorphic Chern-Simons, I'm glossing over some additional subtleties which are interesting, but they are subtleties. We find a 2D IFT. And this is the 2D IFT that we find. So this if you are familiar with 2D IFTs, well, if this is familiar to you, I'd be very interested in talking to you. But for us, this was quite a strange theory. So partial alpha and partial alpha tilde doesn't really matter what they are, but they are just two directions in R2. So they are derivatives along two different directions in R2. This theory depends on two group-valued fields, G and G tilde. And actually, this action has a number of features that are very similar to the 4D IFTs that you get from 6D holomorphic Chern-Simons. So, in particular, d alpha derivatives only appear acting on the field G. D alpha tilde derivatives only appear acting on the field G tilde. This theory is not invariant under Euclidean or Lorentzian space-time symmetries if you consider it on R2 or R11. So, for example, in R11, you could try to say alpha is the plus light cone or alpha tilde is the minus light cone, but you cannot make this Lorentz invariant. You can also, there is another way of thinking about it which also lifts to this 4D IFT story, which you can think of as sort of coupling coupling two 1D IFTs. So you can think of, if I expand out this square, I get a theory which is just d alpha G inverse squared. So that's one 1D IFT sitting along the alpha direction. And I have another one for G tilde sitting along the alpha tilde direction. And I'm sort of building a 2D IFT by sort of coupling these two 1D theories. It's, again, very schematic, but that kind of structure also appears in the 4D Chern-Simons. And I should say that it's that thing it's that property which comes from the fact that you've considered a non-trivial complex structure. So because these fields come from different points on CP1, the complex structure picks out different directions. And that's what allows you to have something that's not just a complexified 1D IFT. So you can compute the equations of motion. You don't get something which is like a normal lax connection. You get something that's more similar to a 1D IFT. In particular, the equations of motion are equivalent to the covariant derivative of B vanishing for all values of the spectral parameter. Nevertheless, you can still use this to construct conserved charges. You can consider the monodromy of B. You can also compute the Poisson bracket of B, and it satisfies Poisson bracket of Sklianin form, so it's ultra-local. So for those of you who are familiar with the space of 2D IFTs, this means that it's kind of on the kind of simpler side of 2D IFTs, which you may kind of expect, because at the end of the day, it is a weird, but it's a very simple looking theory. So, okay, that's the example I want to use, but now I just want to sort of conclude by sort of sketching this relationship between 4D Chern-Simons and 2D IFT and 4D holomorphic BF and the 2D IFT that comes from that. So this is an idea that's been around a long time, but it's known, well, at least certainly for 3D Chern-Simons, and you can generalize it to 4D Chern-Simons, but it's known that starting from the action of 4D Chern-Simons, which I've written again here, you can basically pick out a direction. You have freedom in how you pick out this direction, but we're going to pick it out in this particular way. And you let the coefficient of that field scale with 1 over k. So notice I've introduced a level or a parameter k sitting outside this 4D Chern-Simons action. We're then going to take the k goes to 0 limit. So you can go through the algebra, and what you find is exactly 4D holomorphic BF plus some boundary term. This is the particular form of the boundary term here. And omega, well, I'm not going to expect you to remember the formulae I wrote down, but basically you find that the particular one forms from 4D, the one form in 4D Chern-Simons and the 2D, and the two form in 4D holomorphic BF are related in the following way, and that's exactly what we want to relate these theories. So the first comment is about this boundary term. You may worry about it. It's interesting. It has to be there it has some nice properties, but actually it doesn't change the 2D IFT that you find. So at the end of the day, it doesn't do anything. So we're just going to ignore that. And what you can do, which is construct a particular 4D Chern-Simons setup and a 2D IFT, such that you can basically replicate this limit in all of these different things. So at the level of the boundary and regularity conditions, the level of on-shell solutions, to the 4D Chern-Simons theory, at the level of the 2D effective 2D IFTs, at the level of the lax connection, and at the level of the Poisson bracket. So this is exactly what we wanted, right? This is a relation between integrable field theory that comes from IFT, an integrable field theory that comes from 4D Chern-Simons, and there's a particular limit which gives us an integrable field theory that comes from 4D holomorphic BF, and we can trace that limit through all of these different things. So this is a substantial link between the integrability structures in the 2D IFTs. So just to sketch something, you can kind of see how this would come from a lax equation where basically the component, anything that's linear in B, dominates because it's been scaled by 1 over k, and you've taken k to 0. So the remaining part of the remaining term that you would get from a flatness equation is basically dropping out to scales like k. Yeah, exactly. So if you compute the Poisson bracket, you'll get. So yeah, I didn't say, but this 4D Chern-Simons setup here gives a non-ultralocal 2D IFT. And you can compute the Poisson bracket of that, and it's, yeah, you'll see exactly that delta prime term will scale with k and go to 0. Good. Yeah. So I'm close to time. Yeah. Fine, yeah. So let me just quickly summarize. So I won't spend super long on the what we've done, but essentially, for the 6D holomorphic Chern-Simons diamond, we've constructed this diamond now for various examples, and there are sort of various interesting things we've learned about 2D IFTs. For 4D holomorphic BF diamond, we've now constructed this diamond for a couple of examples, and for both of these examples, we've managed to construct a 4D Chern-Simons 2D IFT setup that has as a limit of that the 4D holomorphic BF 2D IFT, and again it runs through all of these different properties. There are various there are many kind of interesting future directions that one could try to explore. So I didn't mention disorder order defects at all, but the poles that we had in the omega are known as, or the zeros and the poles are known as disorder defects. There are also another class of defects which are known as order defects, where you just couple the 4D Chern-Simons to additional fields, and it would be interesting to see if you can generalize these constructions to the presence of order defects. Something I mentioned at the beginning, can we replace CP1 by some more general Riemann surface? There's been some works in this direction, but it's certainly an interesting question. Can we construct elliptic models, and et cetera, et cetera? So I mentioned that the Poisson structures, I sort of mentioned a bit about the Poisson structures. So in particular, this Poisson structure I mentioned for the 4D holomorphic BF looks very much like a Poisson structure of the 1D IFT. And similarly, one might imagine that the Hamiltonian analysis of the 6D holomorphic BF and 4D IFTs looks very much like the Hamiltonian analysis of 4D Chern-Simons and 2D IFTs. And it'd be interesting to study that in a bit more detail, how they are related. So finally, the bigger sort of questions, can we generalize the limit from 4D Chern-Simons to 4D holomorphic BF to higher dimensions? And can we understand this limit at a quantum level? Is that possible? It's not something we've looked at at all. So I'm just going to finish with a sort of speculative diagram, which I am aware I'm being recorded, but you should, everything up here is very, 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 very speculative. And so these bits in bold, I guess, are the bits that we claim to have some understanding of, and I guess you could imagine going off up into this world. So for 4D IFTs, you may imagine you have a 60 3-Chern-Simons with a 3-form field as well, and who knows, maybe all this is kind of forbidden for another reason, but it would be certainly interesting to explore. So, thank you very much. Good. So actually, this is something I didn't mention. Yes, I mean, in the same way, I very briefly mentioned that you can think of deformations as one way of thinking of deformations is as splitting a double pole into 2 simple poles, and you introduce another parameter. So we did consider 2 examples, which is 3 simple poles and 1 simple pole and 1 double pole. So you can understand this first case as a deformation of this second case, because you're splitting the double pole into 2 simple poles. The limit is subtle. It's not just you need to. It's actually similar to the non-abelian T-dual limit of the lambda model, if you're familiar with that. But yes, in the same way you can try to construct deformations. Good. So the Ward model, which I mentioned, there has been some scattering studied in that, and you get some, I can't remember exactly how it works, but you get some kind of orthogonal scattering, so you get some dispersionless scattering. It's not, things don't just scatter through each other, but you get some nice structure. The other example of a 3D IFT that's been quite well studied is KP, which also scattering has been studied, and you get these nice sort of square wave patterns. There's pictures on Wikipedia you can look at of this in the real world and stuff. So, but I would say quite limited, and there's not many examples of higher dimensional IFTs, and so hopefully this will give a few more, and one can try a bit more systematically to understand scattering.
If I consider this higher dimensional theories as QFTs on their own, is it possible, or have you attempted to compute better functions?
No, that's it. Yeah, excellent. This is not something we've tried. It's something that I've suggested to students, but it's not been tried. The one thing that's probably known as 4D Western-Witten is meant to be one loop exact, and but more generally than that, there is not much. No, or certainly for all the new theories, there is not much that's been done. Be very interesting. No, not at all. Yeah, I think for that one we'd need to look a bit more closely at 4D holomorphic BF and look at the anomalies and try to understand what exactly you need to make sense for it to make sense at a quantum level. Sorry, say again. If you don't take the limit of k goes to 0, yeah, it makes the B field compact in some sense. Oh, I see. What IFT do for that? Right. No, that's not something we consider. So basically, I think that would be some kind of like you would need to include some higher mode expansion or something, or you could think about it that way. No, I don't know. I guess that there have been a kind of orthogonal attempts of looking at understanding 3D IFTs in terms of 2D IFTs by expanding in modes. Fiona and Arkady. But this particular setup, I don't know the answer. Be interesting.
Are there any supersymmetric extensions
Good. So one thing to say is that 4D Chern, well, this is not really answering the question, but so just for context, 4D Chern-Simons comes from a n=1 supersymmetric theory by some kind of topological twisting. By supersymmetry, you mean space-time supersymmetry or targets? Sort of, or no. So one thing you can certainly do is consider supergroups. Yeah, so you can consider supergroups. Everything I said, I guess I was assuming Lie group, but you can consider supergroups, supertrace, and you get theories with, I guess, sort of global supersymmetry, but not space-time supersymmetries. I'm sure there has been something done on world-sheet supersymmetry, but I can't think of the reference if there has.
I have a question. Given, let's say, coming back to the elliptic deformation, if I have elliptic deformation on the P-spark model, for example, as you told, basically Jan deformation, do I know how to retrieve that one from Chern-Simons?
So this was done by Sylvain Lacroix and his master student Anders Warburg. Yes, you can do it, and they generalized it also to SLN R, I think. But you need to take, instead of CP1, you need to take the torus.
And a related question, this construction guarantees me that I will retrieve an integrable two-dimensional field theory. But what about the charges? Are going to be an involution? Is this guaranteed by the reduction?
Good. So there's a group of guys who you know very well. Sylvain Lacroix, Marc Magro, Benoit Vacedo, and Francois Darduc. They have studied a very particular setup where it's quite a broad setup, but it's a particular one where the boundary conditions you consider satisfy some particular algebraic properties, which is this Lagrangian subalgebra story. And in this particular setup, they've shown that you are guaranteed to have all the integral charges. Outside of that setup, this is an open question, and one so far it's I guess a case-by-case basis, but a full analysis I don't know the answer to.
Thank you, Ben. Thanks.
Thank you, Costa. It's a great pleasure to be in Athens again for a workshop. So today I want to talk about some work that I've been doing with Maurizio Firota and Ilias Kiritsis. Maurizio is a Marie Curie fellow in Crete. He's an expert in these things, and basically 99% of this work is his expertise. Good. So this talk is about a rather old subject, about highly excited strings. I would like to argue or remind you that excited fundamental strings are interesting systems on their own, even at the classical level. Essentially because they are systems that have a lot of complexity and very high entropy. And therefore, irrespective of whether you, I don't know, like you want to study string theory or whatever, if you're interested in complicated systems, this could be a laboratory where you can study complicated dynamics. For example, if I have an excited string state at some level n, where I excite accordingly all sorts of harmonics of the classical string, then, as you know very well, the mass squared goes linearly with the excitation level. So it goes like n over alpha prime, where alpha prime is the string length squared. And basically, you can count how many modes you can have that have the same mass. And this is a standard computation that you learn the first days you learn about string theory. And you find that at very large n, it goes exponentially as the exponential of square root of n. So you take a logarithm and you compute the entropy, and the entropy goes like square root of n, which you can interpret back in terms of the mass. It goes like the mass, L string times the mass. You can compute the entropy that corresponds to this, and it's just the inverse, sorry, not the entropy, the inverse temperature is just from thermodynamics, the derivative with respect to mass. And you find that it's a fixed entropy, fixed temperature, doesn't depend on the mass. So you have this weird thermodynamics that is called Hagedorn thermodynamics. Good. So basically, the point here is that if you fix n and look at what kind of strings you have, what kind of configurations you have, there can be all sorts of different shapes and sizes with all sorts of with a lot of complexity if n is very large. Now, another reason to be interested in fundamental strings is an old story that goes back to Susskind in '93, which was further debated by several authors, in particular Horowitz and Polchinski, who clarified it a little bit more. And it's the idea that classical strings, as I said, is a highly entropic object. But we know also of other highly entropic objects that we care about, in particular black holes. So on one side, you can think of these two, at first sight, completely irrelevant systems. One that is an excited string. On the other is a Schwarzschild black hole. Let's say we're in 4 dimensions. And then you can ask yourself, is it possible to connect these two objects? So you can try to do it in 2 different ways. You can start from a highly excited string state, make it more and more massive if you want. So at some point it will stop being classical. It will back react in the geometry, and maybe it will become a black hole. Or you can start with a Schwarzschild black hole and start making the Schwarzschild radius smaller and smaller. And at some point you reach the string scale, and maybe there it looks like a string. So you can do a naive calculation. Obviously, going from one place to the other is very hard because you have to deal with all sorts of dynamical questions. But you can do a naive calculation where you say, OK, I'll take these 2 pictures, and I'll try to just linearly extrapolate them from the classical regime for Schwarzschild black holes and from this regime from classical strings. And I'll try to see if anything matches. And you do this calculation. So you set the Schwarzschild radius to be the string scale. And you set the masses to be the same. And that for G Newton, again, in 4 dimensions, that goes like G string squared alpha prime, you find that there is a correspondence point where G string goes like n to the minus 1/4. So this is also an indication of where your classical string description is going to break down. One way to think about it is as I make n larger and larger, it becomes more and more massive. At some point, I will not be able to suppress G-string effects, and the classical picture is going to break down. But then you compute S black hole, so you plug in RH and G Newton in terms of G-string and alpha prime, and you find that is precisely square root of n. So the two answers match, they don't have to match, but this is a suggestion that maybe in this interpolation, not a lot of things are varying wildly. And again, you can try to compare this with the situation that we have in ADACFT, where we play a similar game. There we have D3 brain, for example, or D1, D5 strings. And we go from a weak coupling description to a strong coupling description. At weak coupling, we have the theory, we have n equals 4 super Young-Mills or whatever, the thing that lives on the D brains. And as we increase, basically in n equals 4 super Young-Mills G-string n, then that description changes, becomes something else, and becomes classical gravity in the appropriate supergravity limit. In that case, so morally it's similar, but in that case we work in an extreme, usually we work in an extremal limit, where we can more easily track at least some quantities from one side to the other, and this is how basically ADACFT works. In this case, in that case, by the way, since we work in the extremal limit, that's our easiest situation, it's hard to discuss the non-extremal case, which will be the more interesting case if you want to do microstate counting of non-extremal black holes. Okay, in this case, you're starting with a non-extremal limit, so you have finite temperature from get-go, and that makes it more interesting. Now, this story is an old story, and it motivated a lot of work in fundamental, people studying the properties of fundamental strings. There is a paper, for example, from '91 of Mitchell and Suborg that studied the size and shape of excited string states by studying the scattering, 4-point scattering with excited strings. There's another classic paper by Amati and Russo who study emission rates and absorption cross-sections of highly excited string states, and then they also had follow-up work on this. I want to stay with the Amati-Russo paper because, as you can see from the title of my talk, I basically want to compute the same things. So what they did in that paper, it's a nice, rather simple calculation. No, it's Jorge. Yeah. So they computed the average, or the averaged inclusive emission rate of massless strings from highly excited string states. So basically, you have this process here, where you have a highly excited string state, say at some level n prime, and that string splits up and emits a massless mode with some frequency omega. So it could be a photon, for example, in open string theory, or it could be a graviton in gravity, and leaves behind some new highly excited string state. So you look at this three-point amplitude process. This is a scattering amplitude, you square it, and then you sum over, it's inclusive because you sum over the Hn, the string that is left behind. So you don't really want to track specific processes of what is left behind. You just sum over all of them at a given mass level. So you fix the mass level, but then you sum over all the degenerate states, the microstates that could appear at the end of the process, because you don't want to differentiate between them. Also, another thing that you do is you have this initial state. It could be a very specific microstate of the string at that particular level, but you also average over all of them. So you sum over them and you divide by how many they are. And basically, after you include some appropriate kinematical factors, you can compute the differential emission rate for this process, and that's what they did. So what they found was very supportive for the previous picture of the black hole string correspondence. So they found that when you do this for open strings in D dimensions here, Imagine that you have compactified, your extra dimensions that you need to go to 10 or 26 dimensions, depending on whether you do bosonic or superstring theory. Then they found that d gamma goes like this. So you have this Bose-Einstein factor here, which reminds you a lot of black hole physics. If you do it for closed strings, you find this expression, which is again the emission rates that you see in black holes. So that was, like a very characteristic result. And then from these emission rates, they compute gray body factors, or if you want, absorption cross-sections, by using the detailed balance condition, which again is familiar from black hole physics, which assumes some kind of thermodynamic equilibrium. Yes? No. What they did is it's precisely what I mentioned here. So they just did this, and they summed over the states in the light cone gauge formalism. Sorry, that's my fault. So that's what they did. So in a little while, I'll show you our calculation, which is based on the imaginary part of the 4-point amplitude. Yeah. Good. Good. So now what I want to do is revisit basically the same calculation, but I want to do it essentially the opposite way. So instead of first computing the emission rates and then deducing from that the absorption cross-sections, I will first compute the absorption cross-sections by using the optical theorem. So I will start from the 4-point amplitude of heavy, heavy, light, light, or heavy, light, heavy, light. I will cut it in the middle, and this will give me absorption cross-sections. I will take the imaginary part in the forward limit, and so that will allow me to compute exactly the sigmas. Then I will use time reversal symmetries to connect 3-point amplitudes, 3-point scattering amplitudes. 1 goes to 2 or 2 goes to 1. And this will allow me to compute emission rates. There are some differences compared to the previous calculation. First of all, this calculation for the sigmas is exact at 3 level. So in other words, I will not make any average assumptions or a large level limit. So it's exact for whatever string state you have. It doesn't even have to be highly excited, which was a requirement in the Amati-Russo calculation. Along the way, we will find something very surprising, which we didn't know about. And we'll talk to people, and some people find it natural. Other people say it can't be right. It's very surprising. We'll find that there is a universality property in the absorption cross-sections, which I will explain. And then we compare with Amati-Russo. We find agreement when omega, the frequencies of the light modes, are sufficiently high, when they're much higher than the energy set by the Hagedorn temperature. But I will call them superstringy frequencies, but for substringy frequencies, the two results disagree. Okay, so one of the calculations is not right. Yes? No. It's what you want to get the sigmas, and then all the rest is how it should be. Yeah. Good. So let me say a few more words here, like a small parenthesis. This subject, as I was saying, like classical string scattering, obviously takes us back to the 90s. For the older ones, it brings back memories. But there have been sort of a revival in this subject in recent years. There has been some nice papers along this direction, papers analyzing the chaotic features of the string S matrix. For example, there was a paper by Gross and Rosenhaus in 2021, and then several papers, some papers by Maurizio, Bianchi, Sonnenschein, Weissman, and other authors that study basically the complexity of string scattering. There have been also other papers where people scatter strings. Strings, again, are massive objects with complicated structure. You would like to see, how you identify this complicated structure in a scattering process and what similarities there are with physical processes, for example, gravitational wave emission. There has also been a lot of work, mostly by Maurizio, on the efficient computation of scattering amplitudes of highly excited string states using the DDF formalism. So we're going to use two ingredients to do the calculation. One is the DDF formalism that allows us to identify very easily highly excited string states, solves the BRST conditions of quantization of the string automatically. And the other one is the coherent state formalism. Okay, so let me remind you of the first technical ingredient here. So I want to write down the vertex operator of the state that corresponds to a highly excited string state. So this is going to be something very complicated. And solving the conditions for a physical state in string theory in a covariant formalism is, let's say, easy in the first few levels, but then becomes increasingly hard. But if you work in the light-cone formalism, then it's easy. Basically, it's a Fock space of states. So you have, you drop the, you only keep the transverse modes of the string. You use the creation operators and just create states easily. The DDF formalism, but then when you do that, you break Lorentz invariance. But there is a way to do this in a more covariant way, which is the DDF formalism, which basically replaces the creation operators of the transverse modes with this new mode that has a Lorentz covariant index. This is a clever way to build an algebra that is the same algebra that you have with the usual creation annihilation modes, but at the same time commutes with Virasoro constraints. And Q here is some auxiliary reference null momentum. And then you can create easily states in this formalism in this way. Basically, you just substitute the usual A with this calligraphic A, and you create states in a similar way. Notice that when we do that, there are two kinds of momenta here. We have this momentum, let's say the tachyonic momentum that you have for the ground state. And then A itself also has some null momentum on it. So the physical momentum is what I call Pn, which is P minus NQ. Okay? And in front of it, you have a complicated polarization tensor. It becomes more and more complicated as you go up in level. Again, this thing, just like, for example, P is not the physical momentum, epsilon is also not the physical polarization tensor. We will see in a moment in an example what is the physical polarization. Now, okay, that's good. I was able to identify the states, but I now want to do efficiently computations with highly excited string states. And I need something that allows me to do that. And for that, we use the coherent state formalism. Dimitris Skleros has done a lot of work on this subject. In the coherent formalism, the coherent state formalism, the idea is basically not to solve for a specific highly excited string state, but essentially exponentiate and build one object with some free parameter. It's basically a generating function that you then differentiate with respect to that parameter, and you get the state that you like. So essentially, we have the ground state momentum, and then we exponentiate this Fock space of states with the creation operators, the calligraphic A states. And you see, we dot here with some free parameters that we later take the derivatives with respect to, and we recover the state that we like. This thing can be rewritten conveniently as an exponential of this type in terms of some polynomials, calligraphic S and calligraphic P. The details do not matter. They are explicitly known. And notice that when I do that process, here when I compute this, the lambdas convert into the zetas. Okay? And this is closely connected with how you go from these epsilons to the physical polarization tensors. So the idea now is the following. Suppose that you're interested in the 4-point amplitude. Instead of taking 4 specific states, now you take 4 coherent vertex operators, and you compute that object once. It depends on the lambdas. And then if you're interested in a particular 4-point amplitude, you just take derivatives with respect to the lambdas and get this. Now, that is going to be complicated, but it turns out that it gives you elegant, in some cases at least, it gives you elegant closed form expressions. So let's look at the 4-point amplitude, which is going to be of main interest for us. Here in the open string case and here in the closed string case. If I took the simplest possible case, like 4 tachyons, for example, in the closed string case or the open string case, then you know the result very well. It's the Veneziano amplitude in the open string case. I wrote it here in terms of gamma functions, and the corresponding one in the closed string case is Shapiro-Virasoro amplitude. Now you compute this 4-point amplitude for highly excited string states. It shouldn't look anything like the Virasoro or the Shapiro-Virasoro. Sorry, the Veneziano or Shapiro-Virasoro. But it turns out that when you compute this 4-point amplitude of coherent states, then the Veneziano amplitude or the Shapiro-Virasoro amplitude factorizes out. And it's precisely the factor that contains all the pole structure of the amplitude. So all the rest, all of the other details that have to do with the complicated polarizations are essentially a dressing factor, which is complicated, but it doesn't have to do anything with the pole structure of your amplitude. And then again, all this case here and all the phis here are known explicitly. So let me give an example so that it's not very abstract. So let me consider, for simplicity here, the 4-point amplitude of a highly excited or an excited string state with a tachyon. The excited string state looks like this. There is a polarization tensor here. You see I have G1 modes of A-1, G2 modes of A-2, etc. And there is some polarization tensor here. This is the state. So what's the idea here? I take the generating functional with 2 coherent vertex operators, 2 tachyons. There are 2 types of lambdas, lambda 1 and lambda 4, for the 2 excited string states. And then I take the appropriate derivatives with respect to these lambdas and contract them with the epsilon that I like, epsilon 1 and epsilon 2. Okay, so that's the general idea. And for leading edge trajectories, wait, what happened here? Something disappeared here. Okay, that's very interesting. Okay. Okay. So what I was going to show here is the case where I take a leading edge state so that it's simple. You see here I activate only A-1, contract with a polarization tensor. And for even more simplicity, just for illustration purposes, I was taking the case where the epsilon, mu1, mu2, etc. is just has a factorized form. So it's basically lambda 1, mu1, lambda mu1, lambda mu2, lambda mu3, etc. So just the product of a single vector lambda. And then what you will find here, hopefully in the slides that are posted, you see a very explicit closed form expression for this generic level state, written very explicitly down in terms of contractions of the polarization tensors with the momenta. Okay. Now, let's go back to our purpose, to our goal. Our goal is to compute absorption cross-sections. That's the first thing we want to do. So again, I want you to focus here. So I have state 1, state 2. State 1, think of it like this. State 1 absorbs state 2, and then it produces something. Obviously, this can happen in many different ways, right? Like I produce 1 state, or I produce 2 states, 3 states, 4 states. But 2 states, 3 states, etc. are down by powers of the string. So at leading order in this string that I'd like to work, I can only, it's enough to consider only processes where I have state 1, absorbs state 2, goes to another state 3. Okay? So I compute the 3-point amplitude, which is in the similar spirit as Amati-Russo. I take this 3-point amplitude, I square it, I sum over all the states in n prime, all the microstates at a fixed level n prime, and that gives me the inclusive absorption cross-section that I care about. Now, how am I going to get this? Since I know how to compute efficiently 4-point amplitudes, I take the 4-point amplitude and I apply the optical theorem to that. So basically, I take the forward limit, I identify the pole, take the imaginary part, and that basically it's a Katowski rule. It allows me to cut the propagator there and get information about the complicated thing that, otherwise I will have to do it term by term, and it's very complicated. Okay, so now I have an expression for the 4-point amplitude. It may be complicated. In general, it is very complicated. I have to take a limit on that, and I compute. Okay, so this is precisely what is written here. This sigma that I care about is related to the imaginary part in the forward limit of a 4-point amplitude, which is essentially this quantity with some kinematical factors in front, and then basically identify the pole and compute. So. So when I do this computation, I start with a generic, this doesn't have to be heavy light or whatever, just like take 2 generic excited string states going to 2 excited string states. This is going to be, in general, a very complicated result, right? Because you have this excited string states, they have this complicated polarization structure. In general, the result is going to depend in a very complicated way on the polarization structures, okay? But then a miracle happened, which we didn't expect. You do the computation, and the result doesn't depend at all. In the forward limit, it doesn't depend at all on the polarization structures. It only depends on the levels. Okay, so all that complicated structure in that limit went away. Okay, and this is what we call the universality property of the scattering cross sections. So. This is just forward limit, 0 transfer momentum. Yeah. And you take the imaginary part. Yeah. Which one? Sorry. Here. No. Yeah. Well, it doesn't have to be. No. Here I'm just doing a generic computation. Right? It doesn't. That's why I'm saying that this is exact compared to the Amati-Russo. I don't have to take any heavy limits. It's just like generic states. They could be light. They could be whatever you like. Okay. So it's generic computation. At this point, I haven't taken any large level limit. Okay. So and indeed, we saw a lot of examples, several examples in the paper where we do low level calculations explicitly without using the formalisms to see if we get the right result, and it agrees with our general result. So that means, for example, that if I average, for example, over the initial states, 1 and 2, okay, it doesn't make any difference because the result, again, averaging over the microstates at specific levels doesn't make any difference because the result is always the same for all the microstates, okay? Okay, so now let me show you what you get, for example, for the absorption cross-sections when you have a light mode. And let's say we go to the frame of the heavy particle, okay? Then for open strings, I get an absorption cross-section that is frequency independent, okay? For closed strings, I get an absorption cross-section that goes linearly in the frequency. Let me remind you for black holes, when I take the 0 frequency limit, sigma goes to a constant, and that constant is proportional to the area of the black hole. Okay, so in other words, essentially, when you do scattering, the size of the target that you look like represented by the scattering cross-section is basically the size of the black hole, the area of the black hole. Okay. Good. And by the way, already here, if you compared with Amati and Russo, you will see that there's a difference. Because there's already, you can see here, when I take omega goes to 0, it's not the black hole result. In other words, there is a non-trivial gray body factor for excited strings. And when omega goes to 0, it's like they have 0 size. Okay. So now let me go to the second part. Now I want to do the opposite. So now I want to compute emission rates. Okay, so how do I do that? Now for emission, you take an excited string state and you want to split it into two. So you have state 1 goes to state 2 and 3. Okay. So you compute the differential cross-section with respect to the energies of one of the produced states. And there are some kinematical factors. It's not important. We have the conservation of energy. And then the whole result is proportional to the 3-point amplitude squared of state 1 going to state 2 plus state 3. Okay. And now our idea was not to use any assumptions about thermodynamic equilibrium, or if you want a detailed balance condition. Our idea was to simply use the time reversal symmetry and relate this amplitude, with this 3-point amplitude, with a complex conjugate of state 2 and 3 going to state 1. Okay. So remember, in the previous, so this was involved in the previous calculation. I had two states, or one state absorbing another state, goes to a third state. And then because I was using the optical theorem, I was naturally summing, it was inclusive, so I was summing over the states. Okay, so I want to do the same thing here. So, I compute now, or if you want, I define a new differential cross-section, which again is very similar to what Amati and Russo. It's the same thing that Amati and Russo computed, where I take that, I take that previous differential cross-section and I sum over the initial, I average over the initial states. Averaging over the initial states is essentially doing the sum that I was doing before in absorption. But I also sum over the final states, okay? Because I want it to be inclusive now as an emission cross-section. Okay, so and here comes the key point. I take this equation here, and basically I do three sums: sum over the initial state and the two final states. That's all I do here. And I take an average with respect to the density of states in its sector, for its state, at its level. Okay, so this is A equals A dagger. I just squared things and I summed. That's all I did. But now notice on the left-hand side, this is essentially absorption, right? So, and there I had noticed I have computed this thing. And I know that it doesn't depend on the details L1 and L2. It doesn't depend on the details on the microstates of the initial states. So I can basically remove these two sums and the two rows because they don't play any role because of universality. And that's precisely what gives me the right hand, this equation here. I removed the sums over L1 and L2. Here I keep the three sums. Here they are. And then I took the two density of states. I brought them on the numerator on the other side. Here they are. Okay. So now I have this left-hand side is equal to this right-hand side. This is precisely sigma absorption that I computed before. And this is now essentially what Amati and Russo were computing. Okay? So in this way, but the universality was very important in order to do this, to be able to do this step. In this way, I can connect my computation for absorption with emission. And now let me show you results. So let me consider the case where I have, let's say, an excited string state. It emits a photon in open string theory. Again, I don't need to take n prime to be very large here, which was part of the assumptions in the Amati-Russo calculation. You get a more exact formula, if you want, that looks like this. The interesting limit here is the limit where the state is highly excited. So I take n to be very, very large, n prime to be very, very large. And also now I have to think about where the frequency of the emitted photon is compared to that. Okay, it could be very, very large and can be computed from this one. But the case that also Amati and Russo very rightly are considering is the case where this is much smaller than the mass of the emitted state. Okay, so in this limit, that rho gets approximated by exponentials, and you get a Boltzmann factor, a dropping exponential, hinting at the thermodynamics of the highly excited string state, with temperature set by the string scale. Now, if you go back, if I go back to this result, this is the result I should be comparing with, it's exactly the same, when you consider exactly the prefactors, all the prefactors match, but, and when you take omega much larger than th, basically you can drop -1 and you get the exponential. All the right, you get the right omega factors, etc. Okay, so the two results agree, but they agree in a limit where omega is super stringy, right? It is much higher than the Hagedorn temperature. Good. And again, the same, and it deviates numerically, not by a lot, by the way, but it deviates when omega goes to 0 from the previous result. Yes. Question. Yes. I think, yeah. I think, yeah. I think, yeah. I have to check if we did it numerically or whatever, but we could check. We could make numerical plots. Okay, now you do the same calculation for the closed string, and it's very similar. Basically, think square. And you go again in the same limit, and you get a result again, not with the full Bose-Einstein factor, but with simply the exponential, which again agrees with all the prefactors and all the omega dependence with the result for Famati and Russo, but not at very low frequencies. And so I'm doing good on that, right? Okay, good. So that's basically the result I wanted to report. It's a little bit surprising, especially this universality property, but it turns out that in the forward limit, things can simplify a lot. We verified again that highly excited string states exhibit a thermal emission spectrum, but now they have non-trivial gray body factors. This is a new result. Also, the universality property is a new result. I have to emphasize here that these computations are possible because of powerful tools provided by the DDF formalism and the coherent state formalisms. And now that we understand them a little bit better compared to the past, I think there is an opportunity to do all sorts of new calculations in this area. Already tree level is certainly possible, and then there are also some higher loop calculations that you might be able to do. And then there are all sorts of physical questions, like gravitational wave of emission or whatever, that you can revisit in this context. And some of these things we are considering at the moment. So let me stop here. Thank you.
Thanks, Vasily. Another question, please.
And you have considered, I think, the scattering of strings on flat microscopy.
Yeah.
Given that they are highly excited,
Yeah.
I was wondering if you can carry over this result to scattering on curved strings.
That's a good question, right? Indeed, one of the first things we were thinking about in the beginning is, Maurizio had all these results with scattering, whether we can do them in non-trivial backgrounds. I think in some backgrounds where, you know the world set formalism, you might be able to do them. I mean, like...
highly excited states that you consider, do you expect differences to be sensitive?
That's a good question. I don't know. There you have more scales, so you might be able to play an interesting game comparing the scales in different ways. Yeah, exactly. Yeah. So, yeah, go ahead.
Is there any connection with Gauss-Mendel?
This is, I think not, because there you're entering the quantum regime, right? Or not? Yeah, you do Heine's, yeah. But we do some similar things where, for example, one thing that we're doing is we're doing scattering of highly excited strings with, say, light modes in the Regge regime in the iconal approximation. And yeah, there we also have some new results for this one. You know that this story is, for example, very interesting even if you do graviton-graviton to graviton-graviton, because you have this iconal resummation and then you have some connection with the shock wave geometry. And we're trying to see if that picture also carries over when you scatter from highly excited string states. So there are all sorts of these things that you can, you can redo, basically. Thank you.
So just make sure that you take your belongings with you because I mean it's not safe to leave it here. So just, and follow some. I mean, some of us like to go to some places nearby, like to get some.